All right, so just to start on, this is the general agenda for what we'll try to cover in the first part of the session. We'll introduce generative AI, we'll understand what large language models are, and most importantly, we look at their cost structures. How do we look at the costing for large language models? We look at the general workflow for large language models, talk about different types of prompt engineering techniques, and uh, the final part, we will look at some hands-on implementations of prompt engineering techniques. So the session will be very, very hands-on, and we look at lots of practical examples and demonstrations in terms of how things will be done. So when we talk about generative AI is not exactly a new discipline. It's been around for a long time, and it all started from the 1950s. The 1950s was a time when the term AI was first coined. Artificial intelligence as a term was first coined in the 1950s. And the whole idea was this was a Dartmouth conference where this term was coined. And a lot of researchers, they came together. And the whole idea was how do we make machines think and act the way humans do? Because 1950s was a very early era. We didn't have any computing devices, mobile devices. There was none of those things that were available around that time. And there was a huge amount of interest in the community where we wanted to we wanted to make machines think and act the way humans do. And that was the origin and that was the inspiration behind the term artificial intelligence. And we are talking about very basic rule-based programs around that time. Machine learning was a concept that evolved a lot later. And if you look at the term AI very broadly, if you look at the term AI very, very broadly, there is one kind of AI which is seen all around us generally today, which is called rule-based intelligence. That is, how do you explicitly make a machine do certain things through hard-coded rules? And that is what I want to start my discussion very, very briefly in the session now. So take an example of a air conditioner. Let's say you have an air conditioner that is running in your room right now, and the temperature is set to 27 degrees Celsius. What does it mean? It means that somehow that air conditioner automatically understands how to adjust its temperature. The air conditioner automatically understands how to monitor the temperature of its surroundings and automatically maintain the temperature at 26 degrees Celsius or 27 degrees Celsius. So there is some kind of a sensor that is present within the air conditioner, which is constantly monitoring at what temperature the room is at. So if the room temperature goes above 27 degrees Celsius, the compressor will stop temporarily. And if the room temperature goes above, it will start. So it is constantly monitoring the temperature of the room. So if your room temperature goes above 27, the compressor will start and it will rapidly start cooling the room. And if your room temperature goes below 27, the compressor will stop. And you would have seen these kinds of auto climate control modes in cars and homes and other kinds of things. If you think about it, this is also some kind of intelligence, isn't it? If you think a little deeply about what exactly is happening here, there is also some kind of intelligence that is working behind the scenes, and that is what we refer to as rule-based intelligence or intelligence that is driven by a static hard-coded rules. That's the way how we look at the term rule-based intelligence. Now, what I wanted to do is I wanted to quickly share across a small snippet with all of you where you can get a deeper understanding of exactly what rule-based AI refers to. Everybody is able to see this, and you can see that rule-based AI is that kind of AI where you tell the machine what to do, how to do it, and the machine does it for you. You provide the set of rules, you provide the set of static rules. You explicitly tell the machine what to do and how to do it. The rules are hard-coded, the rules are static. And that is what we refer to as rule-based intelligence. There are many examples. You can think of a modern day automobile and imagine you are looking at a seatbelt alarm, right? So how does a seatbelt alarm basically work? If somebody wears a seatbelt, if the sensor detects that somebody is wearing the seatbelt, everything is fine. If the sensor detects somebody is not wearing a seatbelt, there's a small beep sound that will continue happening. All of you have seen that. Or let's just say an automatic speed control alarm. So you might have seen there are cases where if the car goes above a particular speed, especially in commercial cars, it happens where the speed limits are up to 100 or 80 kilometers an hour. And if you go above a certain speed limit, the a kind of sensor will be triggered and a kind of beep sound will come up. And there are countless other examples we can continue talking about. Automatic headlamps, which have light sensors, right? Or even in your offices, you go to your offices and there are motion sensors. And whenever a motion is detected, the lights will come up, else the lights will automatically come down. Now, if you think about that kind of technology, it's intelligence, isn't it? It is artificial intelligence. It is some kind of intelligence that the machine has to sense your presence. If something is moving, if I am present, the lights are coming on, else the lights are coming off. There is some kind of intelligence, and that is what we talk about in terms of rule-based AI. And this is what traditional programming helped us do. So when we write traditional software programs, this is exactly what we are doing. We are building systems. We are explicitly writing code. We are writing software using different programming languages. We're explicitly telling the machine what to do and how to do it, and the machine is doing it for us. And that's the way how we look at traditional rule-based intelligence. And there continues to be many applications of this as we speak today. Even if you go to a factory, there are so many machines, automatic machines that are in the assembly line, which are constantly manufacturing products and assembling different types of products. And if you think about it, that is also a classic example of rule-based intelligence. It is not that the machine is able to figure out how to do certain things, but we have pre-programmed instructions. If you look at all the different factory robots that are out there, you look at a car assembly plant, okay, any of the major car assembly plants, if you see, there are so many machines that are operating there and they are doing different things, right? So there's some machine that is assembling the tire, assembling the chassis, assembling the car windows. There's different machines that are meant for different tasks. And if you think about it, there is some kind of instruction that has already been provided in advance. Somebody has written the code. Somebody has explicitly told the machine and trained the machine what to do and how to do it. And the machine is simply blindly following your instructions. And that is, again, what we refer to as rule-based intelligence. So that's the first thing I wanted to start out with so that everybody realizes. And any kind of sensor-based applications that you see, anything where there is a sensor and based on some kind of a sensor trigger, something happens, it's intelligence, but it's a very basic form of intelligence. And this is what we are talking about in the 1950s when we didn't even have the computing devices we have today, right? The world's first computer system was called ENIAC, and that came around that time. So we didn't even have computers around that time, and it was quite a revolutionary thought. Okay, so what changed? What changed from there? If we can write rules to solve so many problems, then what changed? So what changed was people realized that okay, we can solve a lot of complex problems, even to the point of even when personal computers came, we even have softwares that we write today. And whenever you write code in any language for that matter, let's say you write a Python script or a JavaScript or a shell script, or a Perl script. What are you actually doing? Whenever you write a program, what is software? What do we even mean by the term software? Software is basically a set of instructions that you're explicitly giving to the computer, right? Even your operating system is a kind of rule-based AI. Every aspect of the computer, even if you talk about the mobile phone operating systems, every aspect of the way your mobile phone is working is controlled by rules. The rules have been hard coded. Every aspect of the laptop is controlled by rules. And that operating system, the Windows operating system or the Mac operating system, is a very complex set of instructions. Hundreds and thousands to tens of thousands of lines of code, which explicitly control every single aspect of how your system is working. Yes, there are a lot of other machine learning aspects that are starting to come up in operating systems now, but a big part of how your laptop is functioning today is driven by pre-programmed rules that goes to memory management and resource management. Everything is pre-programmed generally. Okay, so sometimes you will see that whenever you open up a very resource intensive program, sometimes your fan speed will increase. Who is controlling that? Isn't it magical? Sometimes when you open up a game or a very intensive application, you will see excuse me, you will see that your fan speed revs up. the fan increases, or the other applications, sometimes it goes to not responding. And who is controlling that? These are all given by rules. So all this was great. Okay, all this was great. Everything was fine. But gradually we realized that rules cannot help us solve everything. This is something we gradually realized, that rules cannot help us solve everything. There are a lot of complex problems that rules cannot solve. And that was a realization that we had generally. There are a lot of complex problems that we cannot solve with rules, especially in the domain of images, audio, video, and text, unstructured data. Let me give you an example. Let's talk about Google Photos for a minute. Okay, so you go to Google Photos, and we can use Google Photos to identify and uh, classify so many different types of everyday objects, right? So let's talk about a simple example of elephants, right? So we can look at a very simple example of an elephant. So what is really happening behind the scenes when you're using Google Photos to identify elephants, right? So let me see if I can bring up a small demo for you. So let me just quickly bring up a small demo for you. I'll open up my Google Photos and maybe show you some examples of elephants, and you can take it up from there. So if you see the screen here, just brought up a couple of very small demos for you here. You can see very interesting. And Google has also very recently modified their photo search actually, so they bring it up in two places now. So one is most relevant. You can actually type text. So they're slowly starting to use Gemini in a big way in their applications today. And so traditionally, and that's a different conversation. But traditionally, what used to happen is you had to search explicitly by those terms. You have to say elephant, sun, moon, like that. But a big part of the search that you can do today is just using natural language. Okay, so it's like you can just go and uh, enter something in natural language. You can just say, okay, I want to see pictures of elephants when I was there in this last year. You can just say something in English, and Google will still return images for you, which is a very interesting thing. Anyways, so what is going on here? Let's talk about it for a minute. So think about it. Can we write a piece of code? Can we write a piece of code to identify elephants? Think about it. So when we looked at rule-based intelligence, as part of rule-based AI, we are supposed to hard code the instructions. We are supposed to explicitly tell the machine everything that we want to do. And that is how traditional softwares are also developed, right? If you look at traditional software development and a large part of the software development that happens today, if you want to create a website or you want to design something, an application, this is exactly what you will do, right? You will get your requirements, you create your design documents, you write your code as per the design documents, because every single aspect of the system is known to you. You know every aspect of your system. If this happens, this will happen. If this is the input, this is the output. Every single aspect of your system will be controlled, right? So the requirements are known to you, and you're simply writing code to make the system do what you want it to do. That's the way how we look at rule-based intelligence. The problem with pictures is there is no one way to identify elephants, right? Think about it. What you're seeing on the screen here, there is no single way to identify elephants. There are so many different ways elephants can look like. Elephants can, may have a tusk. Elephants may not have a tusk. Okay, and you can see very interesting. This elephant has a broken trunk, or at least it seems like that. I don't think this trunk looks like it's normal, right? This is maybe you can see this is a broken tusk. So, so there can be so many different ways elephants can look like. The normal elephant is like what? We have four legs, one trunk, two tusks, two big ears, two eyes, maybe a dark color. That's how we can explicitly identify an elephant. But if you're trying to write hard-coded rules, if you're trying to write rules, and if you're explicitly trying to hard-code rules, how do you then how will you define elephants then? It will be very hard to do that, because some of the rules could be like, okay, if I see two tusks, then it's an elephant, isn't it? Tusk is such a defining factor of an elephant. So it's like so think of rule-based AI as an if-else statement. You're writing an if-else statement. If this, then this will happen. If I detect motion, then the lights will be on. Okay. If the light is less, then the headlight will come on. Rule-based intelligence, if-else statement. So similarly, it's like saying if I see two tusks, then it's an elephant. And there are ways to program it. We can, pictures are pixels, and we can program something based on pixels. But look at the baby elephant here. This is also an elephant, right? So the same rules that work here, those rules will not work here. That's the problem, right? That's what I told you. There's so many different ways elephants can look like that I cannot just have a fixed rule-based criterion. I cannot just say that, okay, if I see two white tusk or teeth, then it's an elephant, else it's not. Because there can be elephants which don't have a tusk, or there can be elephants that have only one tusk. Maybe here it is half broken. You might have an elephant where the entire tusk is broken. And maybe it doesn't even have a tusk, maybe on the left hand side or the right hand side. So there are so many varieties. And if you see here, the legs are not visible. I can only see two legs very prominently, but the other legs are not visible. So does it mean that this is not an elephant? If I see two legs, what do I call it? Do I call it a human? No, of course not. So you can see how difficult it is to actually explicitly write rules for images. Now, elephants we can still talk about. We can debate and discuss about elephants, but it gets incredibly difficult. The moment we talk about other kinds of objects. And let me take an example. Let me take an example with all of you with respect to mountains. Elephants are still maybe something we can debate and discuss. But what about mountains? How do you go and write and identify mountains, right? Look at this, all of you. I've searched for mountains on Google Photos, and there are so many infinite number of different ways that mountains can look like. Okay, so it's a very new feature actually. That's what Google is saying. It's new. This is very recently launched actually. Anyways, so sorry, let me just remove it. I think it doesn't go. Okay, so we mountains can be brown, mountains can be white, mountains can be green. There's so many different ways mountains can look like. Okay, so there's no one way I can write a piece of code to identify mountains. And this is what I was talking about when I'm discussing rule-based AI. So there's no way that you can write a specified explicit set of rules saying that, hey, this is mountains, this is not mountains. Impossible. Mountains can be green, mountains can be brown, mountains can be white, mountains can be, they can have a triangular kind of shape, they can have this kind of a shape, or they can just be plain flat. Okay, mountains can also be plain flat. And just no way, there's just no way that you can explicitly write code to identify mountains. Okay, so what I'm getting at again is there are a lot of applications where you will see there are a lot of applications, real applications where you will see that it is very hard to program rules. And if you take this conversation to audio data, speech data, I was discussing the transcription use case with all of you. If you take this example to speech kind of data or audio kind of data, it is very difficult to do that there. There also it is extremely hard to do. Okay, imagine I'm saying something and the meeting transcriptor is trying to convert my entire speech into text. Speech to text is impossible to do using rules. You cannot define hard-coded rules. You cannot explicitly tell the machine that, if the audio is like this, then the text is like this. It's impossible. Even simple things like the way Google recognizes our speech, like even something like when you say, okay, Google. So Google is trying to recognize, actually my Google also fired up now as I said it, but think about it. There's so many infinite number of ways we can say, okay, Google, right? Think about it. So when we say, okay, Google, it is not, it is not just one way we can say, okay, Google. There are infinite number of ways I can use that term, right? So how do I pre-program rules? It is impossible. It is very difficult, and it is literally impossible to pre-program audio signatures and say, okay, if the audio is like this, then it means this. And if the audio is like this, it means this. And it's just impossible because there's so many varieties and there's so many infinite number of ways things can happen. And that is where the challenge of rule-based AI comes in unstructured data. That oftentimes the rules are hard and the rules are unknown. We don't even know what the rules are. Sometimes the rules are hard, like for elephants, they're hard. And sometimes we don't even know what the rules are, like mountains. What rules do I write? How do I even know what is a mountain? You can take a picture in the middle of a green rainforest, which is up on a mountain, and Google will still know it's a mountain. There is nothing that tells you it's a mountain, but the model will still identify it's a mountain. So these are things that are impossible to hard code generally. So how do we do that? Now let's come to the conversation on machine learning based AI, right? So this is where people realize that we cannot design AI systems just using rules. We need to design AI systems. We still want to make machines intelligent, but now we want to make machines intelligent using something else called machine learning, where we want to make the machine learn the rules. We do not want to explicitly hard code the rules, but instead we want the machine to figure out the rules. We want the machine to figure out what the rules are. And that's the way we look at machine learning. A very simple application of machine learning is as follows. You can actually see how machine learning happens through this very small demonstration here. All of you can see this one. So see, this is the input and this is the output. And what we do in machine learning is we give the machine lots of input-output combinations, input-output examples. So we give the machine lots of input-output combinations, X, Y, X, Y, X, Y. So we show the machine a lot of data. And the machine learns the patterns. The machine learns the rules from the data. That's the way how we look at machine learning. So we give the machine lots and lots of data, and the machine learns the patterns. The machine learns the rules from the data. That's how we generally look at the term machine learning. That's how we look at it overall, what machine learning is all about. So give the machine lots and lots of data, lots and lots of historical data, XY combinations, input output combinations, you show it, uh, and the machine will learn the rules from the data. So if you see the screen here, 1, 2, 3, 4, 5, 6, 7, 8. So we are giving the machine lots of historical data, how the inputs and outputs look like. So how the inputs and outputs look like. 1, 2, 3, 4, 5, 6, 7, 8. So the machine will learn the patterns, or it will learn the rules from the historical data, and it will learn the rule as y equal to x plus 1. So what is the rule the model will learn? It will learn the rule y equal to x plus 1 based on the historical data. And based on the rule it has learned, next time I give it an input 9, it will predict an output 10. Okay, so 1, 2, 3, 4, 5, 6, 7, 8. So it will learn the uh, rules from the historical data. Okay, it will learn the rules, which is nothing but a function, or it's a model. So if we build a model from the historical data, whatever historical input output combinations we have, we learn the rules from that. And next time we have a new input 9, the model will predict an output 10. So this is what will happen based on the historical data. Okay, and then there are two very, very important terms that we use in machine learning. And as again, one is called model training, which is called dot fit, right? So you give the machine the historical data and you train the model. So when we say training the model, what it means is you have the historical data and we will use some kind of algorithm. We will do a dot fit and we will build a model. This is called model training. From the historical data, do a training. That means do a dot fit and build a model. This is the part where you learn the rules. And I hope everybody understands the difference. So in rule-based AI, this is something we were hard coding. We were explicitly telling the machine, if the input is this, the output will be this. We humans, we had to study the characteristics of the system. That is what software developers do, right? When we collect requirements, that's what we do. We go through the system requirements, we understand each and every aspect of what is to be done. And we write rules, we write the program, we write the code in whatever language we have to, right? That's what you do. When you create a website, you are actually collecting the requirements from the client, every single aspect of it, what the way the text box will be, what the color will be, and that is what you're going ahead and programming, you're coding, you're hard coding it. So every single aspect of traditional software development is hard coded. But if you look at machine learning, we are not hard coding this rule. This rule is completely learned from the historical data. 1, 2, 3, 4, 5, 6, 7, 8. Give the machine lots and lots of historical data, use an algorithm, and based on that, we will end up building a model. The model is nothing but the rules or some kind of a mathematical function. This is what we call model training, and this is also done using some kind of a fit. It's also called fitting. There are a couple of interchangeable terms that we use. And if you see, there are three very important terminologies that we used here. One is the data. This is the training data. There is an algorithm. We are using an algorithm to train on the data, and in the process, we are building a model. So there is data, there is algorithm, and there is model. So dot fit, model training, and then once we have trained the model, once we understood the patterns, given a new value of x, we will predict what is the corresponding value of y. That is what we call dot predict. So this is how the entire workflow typically happens. And if you just to summarize, if you see, this is what we are doing. We take some data. This is what we do in machine learning. We take some data, we give the machine lots of input output combinations, and the machine learns the patterns using different algorithms. So if you look at the traditional machine learning field, there are different algorithms that exist in machine learning. So once you give your input output combinations, your XY patterns, there are different algorithms that are there, like logistic regression, decision trees, random forests. Many algorithms are there, and those algorithms are used to learn the patterns from the data. Those algorithms are used to learn the rules, learn the equation, and based on that, we end up building a model. We end up building the function. And once we have the mathematical function, using that, we can predict, given any new x, we can predict what is the y. This is the workflow. Okay, so this is how machine learning is different from the traditional rule-based AI, and it is dynamic and it is error-prone. As you can see, it's not hard-coded. So the rules are not exactly static. The rules are dynamic because it is learned from the data. And as you can imagine, if the data changes, if the underlying data changes, let's say whatever data I have today, like these XY combinations, tomorrow I would have generated some new data. Day after tomorrow, I would have got some new data. So every day the data is changing. And as the data is changing, similarly, the rules or the patterns are also changing. So that is why we say in machine learning, the rules that are learned are dynamic. The logic that is learned is dynamic. Whereas in traditional rule-based intelligence, the rules are static. Unless we change it, the code will not be modified. But here, the code is kind of modified automatically because the machine is constantly figuring out the rules from the incrementally generated data. Of course, that's model retraining that has to be done. And to extend the conversation, there is something called deep learning. Going back to our slides, if you remember, there's something called deep learning, and that is typically a subset of machine learning. So we talked about AI, we talked about rule-based intelligence. That's a way of doing AI, and we can also design intelligent systems using machine learning. And a subset of machine learning is deep learning. There's a term DL I have consistently used. So the idea is very similar. The idea of DL is again very, very similar. Here also we have the data. We give the machine lots and lots of historical data. The only difference is deep learning has specific algorithms. There are special algorithms that are used to learn the patterns, but the end result is the same. The end result is we end up getting some kind of a rule, model, or some kind of a mathematical function that associates the relationship between X and Y. Okay, that is giving us some kind of an association between the input and the output. So the idea of deep learning is exactly the same. Here also, we give the machine lots and lots of data. The machine uses deep learning algorithms this time, which are actually neural networks. This is neural networks, and those kinds of things are used to learn the patterns, learn the association between X and Y, and the end result is some kind of a deep learning model, rules, or a mathematical function. So the end result is again some kind of an equation, or it may be an equation form, may not be an equation form, but this is the way we generally understand the terms. Okay, so then you might be asking a question that, okay, then why do we use deep learning if we already have machine learning, which is learning the rules? Then why is deep learning used? So deep learning is generally used in cases where we have unstructured data. So deep learning works very well, and deep learning scales very well, especially for unstructured data. So if we have images, audio, video, or text kind of data, then deep learning scales very well. Okay, because the patterns are more complex. I was talking about Google Photos, like if you remember, this was the example that I was showing you. So if you think about this kind of a system, if you think about this kind of a system, this is actually again working completely on the basis of deep learning. If you think for a minute, how did Google design it? Because right now, what we are seeing is prediction. Right now, what we are seeing is model inference, model prediction. So given a picture, we are trying to predict, okay, is it a mountain? Is it an elephant? That's what we are doing, right? When we type something here, this is like model.predict. But the model has already been trained. Google Photos already has a model that has been trained behind the scenes. Now, all that is happening is next time I click a picture, next time I take a photo, Google is simply going ahead and predicting that, okay, given this new image, what is it called? Is it a mountain? Is it an elephant? Is it this? Is it that? That is all that is happening right now. So Google has spent a lot of time and effort and resources to train this model first. They would have collected lots and lots of sample data. So even before we come to this step, Google would have collected lots and lots of data. So they would have trained the machine with lots and lots of historical image data, and and these are pictures like these are like, okay, pictures like this are called mountains. This is not from my photos. Google will have their own repository of images, and where they will train the machine very similarly like how we looked at here. So they will train the machine this way. They will say, okay, these are images which correspond to mountains. These are images which correspond to elephants, and these are pictures which correspond to trees. So the X will be a picture and the Y will be a label. So you will show the machine lots and lots of images, right? So you show the picture, lots of pictures of mountains, and say it's a mountain. You'll show the machine lots of pictures of elephants, and you will say it's an elephant. and you will show the machine lots of pictures of trees, and you will tell the machine that, what is called a tree. This is how you're teaching the machine. You're providing the input output combinations, and the machine is figuring out some association, and it is figuring out some rules based on the data that you're providing. And then there are other ways to form those rules as well. Those are technical aspects we are not getting into. There are neural networks that are used for it. But the end result is there is some kind of an association. There's some kind of an equation we learn. There's some kind of an equation between the label and the pixels of the image that we are able to kind of learn at the end result. So the machine is able to figure it out. Not that we are hard coding, but based on the data, the machine figures out some association. And next time I give it a new image, the model predicts that that new picture is an elephant or a mountain or a tree, whatever that is. And that's the way how we can think of traditional machine learning. Okay, I hope everybody's getting a sense of traditionally what machine learning is basically all about. So that's exactly what's happening here also. If you think about it, that's exactly what's going on here as well, where we look at a picture, and next time you click a photo and you look at an image, Google is also trying to effectively predict what that picture is called. Is it a mountain? Is it a tree? Is it a photo? Because they already have a model that is built. And that model is also constantly evolving. Not every day, but Google will have their own retraining frequency. Every day, mistakes will be made. And that is the other important thing about machine learning. Sometimes machine learning can be prone to mistakes. It is not guaranteed to be always 100% accurate. Now here it is working fine, but there are a lot of cases where the answers may not be fine. Okay, for example, Google has made a lot of embarrassing mistakes in the past. Okay, and if you see, it has actually a lot of times it has actually made some mistakes. Okay, it actually even recognized people as gorillas at times. Okay, by mistake. Okay, so there was a very infamous incident that happened where where Google uh, misclassified misclassified a black person to be a gorilla. Okay, so this happened some time back where uh, you know uh, let me bring it up. Let me quickly bring it up. Excuse me. So this was a real incident that actually happened. You can see the bottom part here actually. So you can see the bottom part of the image here where this is a real story where Google misclassified the black person to be a gorilla actually. So what I'm getting at is machine learning is not always 100% correct, not always 100% accurate. And if you think about the reason why this happened is because the machine was trained in a very biased manner. So the data that is taken is very, very important. Whenever you train these kinds of systems, it is very important to collect the right kind of data. Okay, so maybe here one of the things that happened was while training this kind of a system, the machine was shown lots and lots of images of black, animals, and the machine was shown lots and lots of examples of white humans. Okay, because Google is an American company. I'm just giving an example. It doesn't have to be that way. And this was long back. This was more than 10 years back that this happened. So maybe the sample set of humans that they had were all whites, and the sample set of gorillas they had was all black, because I don't think gorillas come in any other color. So it's like saying that, okay, anything which is black is a gorilla, and anything which is white is a human. So your data itself is like that. So next time a black human stands and takes a selfie, Google says you're a gorilla. Okay, because it is just doing classification that way based on what it has been trained on. Okay, so this is the other aspect of machine learning, that oftentimes machines can end up making mistakes, right? And you can see there are some biases. There are some inherent biases that constantly happen, right? For example, this one. So Google understands that whenever you wear this kind of a hat, is related to graduation. I think even as humans, we kind of we kind of have a similar kind of association in our heads, because we have also seen similar kinds of graduation photos in movies, in TV serials, and all that, right? So that's how we humans learn the same way. If you look at humans, we also learn the same way. We learn from examples. See, it may not be graduation, it may be something else. But based on our association, based on our understanding of how things are, it seems to be a graduation. So that's why when we look at this image, we say it's a graduation based on how we have been trained, based on our data. That's the way to look at it. Okay. So this is just to introduce the idea of what is machine learning at a very, very conceptual level. And just a final example, all of you can see, this is what I was talking about, how humans learn and how kids learn. Okay, humans learn the exact same way. When we were all young, when we were all attending school for the first time, we were all taught what fruits are, what the different types of fruits are, and how fruits look like. Okay, so somebody had to tell us that, okay, these are how apples look like, these are how mangoes look like, these are how guavas look like. Somebody has to teach us, right? And this is exactly how the data looks like. So somebody has to show us lots and lots of examples of fruits and say, okay, you know what? Fruits like this are called apples. Fruits like this are called guavas. Fruits like this are called apples. And fruits like this are called guavas. So somebody has to show the fruit and then say it's called an apple. And that is how the kid learns. That is how the child uh, forms an association between the picture, the pixels in the picture, and the label, what the label is actually called. And that's the way how real world machine learning, and that's how humans also learn in some way. So humans learn the same way, uh, machines learn from lots and lots of example data. Okay, so if you are not taught about some kind of fruit, you will never learn. If I show you lots of pictures of apples, if I show you lots of pictures of guavas, you will learn very well. But if I don't teach you what is a jackfruit, or if I don't teach you what is a dragon fruit, I don't think in very early age people talk about dragon fruits. It's only like first 2 days in school, maybe the teacher will teach you about apples and guavas. So the kid will learn that. The kid will learn what is an apple and what is a guava. But the kid may not know what is a dragon fruit, and the kid may not know what is a jackfruit. So that's the way to look at it. So the machine is only as good as the kind of data that you have used to train it. Okay. All right. I have another very nice animation and a very small demonstration that I want to do with all of you. This is to further give you a very nice understanding of how machine learning actually happens, how machine learning actually works behind the scenes. So there is a website called Teachable Machines. I'll take you there, and I wanted to demo this machine learning for all of you. It's a very nice animation. The Teachable Machines is a very nice animation. So there it is, and you can actually see the entire machine learning piece in action, pretty much whatever we talked about. So we can take a small image project, and what I will do in this is I will take some examples right now. So let me just create two classes. So I will create a class which corresponds to a, let's say, a remote. Okay, so I'll hold up a remote, and in the other hand, I'll hold up something. What do I hold? Let's say I hold up a water bottle. Okay, a bottle. Okay, so let me take those two objects here. Then, and what I will do is I'll try to demo this to you real time, exactly what is happening. Okay, so we all understood rule-based AI. We all understood in rule-based AI, we are hard coding the rules. Okay, we are studying the system, we are hard coding the rules, and you will see in machine learning how the machine is learning the rules. Here, you're not hard coding; you're simply showing the machine lots of examples. Okay, so let me turn on my webcam and let me quickly show you how this looks like. So we have got lots of. This is the remote I'm holding right now. So this is how the data is collected. Can you see? See how I collect lots and lots of examples of remotes. I'll quite literally rotate it. Like see. And it's very important to show the machine different examples, like the remote can look like this, the remote can look like this. It's important to hide the name Samsung, let's say. It doesn't have to be Samsung. So I don't want the machine to associate Samsung with the remote. So you try to show as much of variety. It can be a very close-up view of the remote. See, like this. Even if I show it something like this, it will know it's a remote. Even if it sees this, it knows it's a remote, right? Even if I show the backside, very, very zoomed view, it should know it's a remote. So see, there are so many different ways remote can look like. And I've already shown 393 samples by now. And similarly, I will show the machine lots and lots of examples of how water bottles look like, right? I'll show the machine lots and lots of examples of how water bottles look like. You can see. So the bottle can look like this. The bottle can look like this. The bottle can look like this. There's so many different ways bottles can look like. So I have to show a zoomed in view, right? Maybe just a cap. Maybe this. Okay, you can see how bottles look like. Okay, you can see this. So 390 examples, approximately that. This is a very balanced kind of example I've taken. So there are around 390 examples of uh, remotes I've shown, and there are around 390 examples of bottles I've shown, all very varied pictures. And this is the very important criteria in machine learning. You have to ensure that the images are very varied. There are different varieties of remotes, and there are different varieties of bottles. The pictures are very varied. That's what we have here. And now what we will do is we will go and train the model. That's it. This is the part where the machine is learning the associations of the from the inputs to the outputs. That is what is happening right now. So it is building a model, and you can see it takes a while to train. And after that, we can do predictions. We can actually do the predictions. So next time I show it any new picture, the model will be able to predict what is that picture. So this is machine learning. This is effectively how things were happening in traditional machine learning terms. Okay, and now you can see that this is I can hold up a picture of a remote. This is what a bottle looks like. You can see no matter how I hold it, the machine still knows it's the bottle, and I can hold up a remote, and the machine knows it's a remote. See how prediction and inference is happening. Even if I do it this way, the machine understands and it's learned pretty well it's a remote. Even if I give a zoomed in view, it knows it's a remote. If I show it just a picture of the cap, see it knows it's the bottle. See how beautifully it has learned it. This is what machine learning is all about. Okay, and if you think about it, it's extremely powerful. It's extremely powerful because it's very hard to uh, it's very hard to otherwise do this thing in practice. Very hard to do it in practice because there's no way you can explicitly hard code or define the rules. And that's again one of the areas where machine learning helps us. Okay, so I hope everybody is generally okay and clear with the concept and the evolution of these different jargons. AI, machine learning, deep learning, which is a subset of machine learning, and from that generative AI followed. So this entire conversation was to help people appreciate that Gen AI is not something that came out of the out of nowhere. So Gen AI has evolved, and that is why we say that anybody having some prior background in AI and traditional machine learning, deep learning can relate to this domain a lot better. It's not a prerequisite skill, but if you already have some prior background of the traditional stacks, you can relate to generative AI a lot better because the components are all very similar. The components that we use in Gen AI and the architectures in Gen AI are all coming from machine learning and deep learning, and the ideas are very similar. So what is generative AI? How do we look at generative AI? Here, there is no, so the machine is not trying to do some prediction based on patterns it has learned. The machine is in a way trying to generate something entirely new. So the machine is in a way trying to generate something entirely new. And that's the way how we look at the term generative AI. So unlike in traditional machine learning, once again, what we are doing, we are having lots and lots of historical data. We are training the model with lots and lots of historical data. And the machine is learning the patterns from lots and lots of historical data. That's what's happening generally. But in generative AI, what's happening is, yes, there is historical data. Yes, there is still model training that is happening, and we'll see some of that as we go along. But in this case, we are ending up generating something completely new. It is not looking at a picture and trying to classify, is it an elephant, is it a tree, or is it a cat? But in generative AI, we are trying to generate a new picture of a tree, a new picture of a cat, a new picture of some kind of text. So we are trying to look at existing data, and we generate images which are similar to the ones that we train the machine on. And it doesn't necessarily have to be only images. It can be text, it can be videos, it can be audio, and it can be any other form of data as well. So we look at the historical data, we train the machine on the historical data, and on the basis of that, we try to generate content very similar to the original content. Now, when we talk about generative AI, there are effectively two very uh, broad categories that usually come up. One is large language models, which is going to be a big focus area generally for us. And the second is what we refer to as large multimodal models. So first we have large language models, and these are Gen AI models that are pertaining to language data primarily. So they are trained using language models. And the primary objective of these large language models is to predict what is the next word in the sentence. So in a way, they are trying to, they are basically word prediction engines. I give you a sequence of words, I give you some text, I give you some sentence, and you're trying to predict what is the next word in the sentence. What is the next word in the sentence? And then you're using that to predict the next word in the sentence. So that is traditionally how large language models have always evolved. And even if you look at a GPT, a chat GPT today, how a chat GPT typically gives answers to questions, you ask it a question, you write a prompt, and you will typically see that the text is generated word by word. Not entirely word by word. It's actually so fast that you will not be able to see. Sometimes it's a word, sometimes it's an entire phrase, but you will still see there's a very sequential way how the content is generated. And that's a very important thing to keep in mind, that when these large language models are working, they are actually trying to look at the entire sequence of words or the entire sequence in the prompt or the question that you asked, and they're simply trying to predict the next word. Based on that, the next word. Based on that, the next word. That is what is going on behind the scenes. I'll show another demonstration of how this is happening in a bit more detail in a while. And the other kind of model, the other kind of category is large multimodal models, which are slowly starting to evolve in a big way today. Because if you look at all the general uh, models that are coming out today, they are mostly all multimodal models. This trend started especially from last year. So until last year, we only had large language models, and this is how the domain evolved. They were only working with text data. You give it an input text, and the model was giving an output, text. But what we have today, especially with all these newer trends like the ChatGPT, Ghibli style, Ghibli Studio pictures, and Google also has recently, you know, uh, released a very, very new image generation model. So what you can literally do is you can type a text and they will generate an image, or vice versa. You input a picture, you can input a file, you can upload anything, and you can generate anything out of it. So that is what is going on behind the scenes when we talk about large multimodal models. Okay, so these are the two broad categories what we have generally seen. Although this is a very, very new area, it's mostly what you will see. A lot of what you will generally see is large language models in action. Okay, now, so what I have in this slide is to highlight some of the general application areas of LLMs. Now, there can be other broad categories we have, but I've generally seen that all the application areas can broadly be stacked into these five categories. Generally, whatever use case you're working on, whatever application area you're working on, can be broadly stacked into these five categories. First is classification, question answering, summarization, code generation, and creative generation. So what is classification? Let's start with it one by one. And any business problem that you have, any use case that you have, uh, will generally be part of any one of these five categories. Any application, you can think of any general application, it will usually be a part of any one of these five categories. So first, let's start with classification. What is classification? Classification is where we look at a picture. Classification is where we look at a picture and we try to classify uh, what is the object in the picture. That's what we discussed in the Google Photos example. Now, aligning the conversation back to text, because now what we will do, we are discussing large language models. Major part of what we'll talk about, and mostly what we'll talk about from here onwards will be LLMs. So bringing our conversation back to text, what could be an example of classification for text data? So we look at some text and we try to predict what is the sentiment of the text. So I give you some review, let's say, and based on the text of the review, you try to predict what is the star of the review. Is it positive? Is it negative? Okay. So we look at the text of the review. So based on the review text, so we look at the text of the review. Based on the review text, we try to predict if the sentiment is positive or if the sentiment is negative. We try to predict the sentiment of the review based on its text. That is what we call classification. Another good example could be we look at some kind of technical documentation, because the organization here works with a lot of technical documentations, right? So we can look at your technical documentation, or let's say there's some support ticket that is raised. Somebody has raised a support ticket. So we can look at the content or the text of the support ticket. And based on that, the model will classify what category that ticket belongs to. Okay. So what support category that particular ticket belongs to? So we can look at the text of the support ticket. We can look at the problem, and based on the text of the support ticket, the model can classify what category that particular support ticket belongs to. So these are all examples of classification problems. Based on some input, we are trying to predict some output from a known set of outputs. So let's say if we look at sentiment analysis. Now, sentiment can be either positive or negative. Users, you buy something on Amazon and you go to Amazon and you write a review, right? So your sentiment will be either positive or negative. Either you are feeling good about it or you are feeling bad about it. There can be nothing in between, right? Or maybe there's something or neutral, whatever. So it's only from a set of known categories that we are trying to do a prediction. So from a set of known categories, we are trying to make a prediction. Is the sentiment negative or is the sentiment positive? That's the way to look at it. So that is how we look at a classification problem. That's the way how we understand the classification problem, that the model tries to predict something out of a set of known categories. Then we have something called question answering. And classification, although I wouldn't call it a traditional generative AI use case, because classification problems is something, and some of you who are coming from the world of traditional ML and DL, you can relate to it that we can already do classification using traditional approaches, right? And it is doable. We can very much do classification using traditional approaches. We can use traditional machine learning, count vectorizer, bag of words, right? Or we can use deep learning, RNNs, LSTMs to classify things. And these are all solved problems. It's not something that is new. We have been doing sentiment analysis for more than multiple decades now. It's not something that is new. But we have generally seen that with LLMs, these tasks are done in a more accurate way. They are done more efficiently and in a more accurate way. The accuracy of the tasks are generally more when we use large language models for these tasks. So when we see some of the demos on classification in our session, you will realize that the same sentiment analysis, the same product categorization, the same support ticket classification use cases can be solved using machine learning, and they can also be solved, using generative AI. So both the approaches can be used. Just that with Gen AI, we can get a higher accuracy and we can do it better. This is something that we have generally observed. Second category is question answering. Question answering is again something that is not new. We have done question answering. We had the technology for question answering uh, much before Gen AI. Today it's a big hype, I know, but even if you look at 2014, 2015, around that era, we had question answering systems even then. LSTMs were used, long short-term memory neural networks were used for question answering. You give it some question, you ask some question, and model was able to generate a sequence of responses. Okay, so this was not a new thing, but again, with generative AI, these kinds of things are done in a better way. Even with transformers, 2017 is when a transformer architecture was invented, and question answering was very popular that time. It's not something that is a new fashion today. These things were there that time as well. But just that with Gen AI, with the large language models, we are able to do it better. Okay, I will not talk too much about the architectures and all that because the focus is more on use cases for this part of the session. But because architecturally, once you take a deeper look at these LSTM models, these transformer models, you will realize that we have the technology for all this. But the large language models are able to do it better because we use pre-trained models for these tasks. Summarization is also something that is not new. We were able to do summarization before also. 2018, we had something called BERT, transformer-based architectures, and summarization was done very well using those kinds of models. There were a lot of applications with summarization around that time. But again, with large language models, we are able to create summaries in a much better way. So you have it's almost a household application today. Anybody can be part of a Zoom meeting. You can do a Google Meet, and you can record the entire conversation. You can generate the transcript of the entire conversation, and at the end of it, the transcript can be summarized. The entire conversation can be summarized in let's say 100 words or 200 words. So summarization is a very common application today. Nowadays, you even have call summaries. Okay, even Truecaller has this feature. In Truecaller, you can record the entire call, the entire conversation, and your entire conversation will be converted to text. So let's say you have a big conversation you have with somebody. So you can record your entire conversation, and the whole conversation will be converted to text. And at the end of the call, Truecaller will generate a summary for you. It comes as part of Samsung. If you have a Galaxy device or maybe even Apple device, I'm not sure Apple how they do it, but in Galaxy, I have a Galaxy phone, and in Galaxy also you have this kind of a feature. They use Galaxy AI to do call assist and call recording. So you can record your entire call. It will be transcripted, and then and at the end of the call, the summary will be given to you. So once you have that entire text, you can summarize and you can find out key action items and all those kinds of things. So summarization is also something that is not new. It is not a new use case, but we see a lot of applications. It's done in a better way today. Okay, and as we get deeper into the sessions, we will talk more about business specific use cases. But right now, I'm just generally discussing. So there can be many practical examples of summarization from a business perspective. Some applications are obviously recording the meeting, recording the meetings and creating a summary. It could be looking at a big technical documentation and creating a summary out of it. Okay, so let's say there are a lot of issue logs that you might be having. A lot of customers will come back to you with a lot of issues, and you will have a big documentation in terms of what kind of issues you're solving, right? And you don't need to go through that entire 1,000-page document. You can rather take a small summary. You can rather work on the basis of a small summary. That's the way how the summarization models can work. Summarization models can be very useful in the legal domain. That is another area where we see a lot of this is picking up in the legal domain, where typically the documents are very big, they're very long, the text is huge, right? And if you look at lawyers, they will have to sift through multiple documents. They will have to look at past case histories, and there's a lot of text data that we are usually working with in the legal domain. So summarization is a very good use case in those kinds of areas, I would say, where you can literally look at a past judgment, let's say, which is spanning 1,000 pages, which is very normal in legal domain to judgment, 1,000-page judgment, 10,000-page judgment is very normal. Okay, you can look at a entire judgment and you can try to summarize that in a matter of, let's say, 100 to 200 words. Only look at the specific key phrases, and you can see how helpful this kind of a thing could be for lawyers and judges, to take decisions. It is not to say that AI will replace everybody, but it is to say that AI will make people more efficient. AI will make the processes more efficient. Okay, it will make the judiciary more efficient to focus on things that are actually important. Okay, so next time when you're in a courtroom, and if you've ever seen a live courtroom proceeding, and all the courtrooms, many of the courtroom proceedings are recorded nowadays, right? So you can actually see that the lawyers and judges, they waste so much time, like uh, you can actually Google out today Supreme Court. You can see some live courtroom recordings. You will see how much time is wasted by, people are going through documents, people are reading article number this, article number that. So there's so much of time that gets wasted through all these references. So AI can actually help in a big way. If there are ways we can summarize it, if we can build a question answering system, so AI can scan through those 10,000 pages. You don't have to manually look up, but the AI system can go and retrieve the answer to your questions based on what you're asking at that point in time. Okay, so that these are some of the good applications we can look at. Yeah, technical support documentations are also very good. So okay, so let's say you're working on some product, okay, and you ship your product to some customer, and typically the technical documentations will be very big. But what you can do with summarization, you can summarize it to only a few pages, so that the customer has the most up-to-date information in a very summarized manner. Okay, the same also applies for a lot of contracts we sign on a day-to-day basis. This again borders on the legal domain. But next time you open up a bank account, there is always a terms and conditions sheet, right? It is that dreaded TNC, the terms and conditions section. You want to take an offer, or you want to open a bank account, you want to take a credit card. For credit cards and all, there is an MITC, most important terms and conditions and all that, right? So it's very hard. It's very big, no? I mean, if you see that booklet is usually like 20, 30 pages, it's huge. Now, nobody has the time to go through all that. So these are again very classic use cases, which even something like a ChatGPT today is able to do very well. So today you can literally download that MITC, upload it on ChatGPT, and ask it to summarize it. These are some very good applications of summarization that from a day-to-day perspective everybody can start using, and of course from a business perspective also. Okay, or maybe even question answering. We can extend the use case to question answering. What you can also do is you can go and upload that terms and condition sheet, and you can start asking questions. You can say that, hey, when was the last time this happened? Okay, let's say you buy health insurance. There's so many clauses. There's so many potential clauses in a health insurance, like how much of co-payment, how much of there's a lot of hidden things that are there, which are usually part of the terms and conditions section. Okay, and it's very important because when we get hospitalized and when we want a claim, we want things to be processed seamlessly. That time we don't want issues to happen, right? So it's very important to like understand every single aspect of the terms and conditions part. Okay, so you can potentially think of a question answering system where normal users can upload their health insurance documents, and they can ask a simple question and they can get an answer back. Now these are some very revolutionary applications that were not there before. Yes, we had general question answering systems, the kind of thing I'm talking about today. It's much more accurate with LLMs and with the powerful language models that we have today. It's a lot more accurate. They're able to give you the answers in a much more accurate way. And it's an evolving system. It's an evolving system. It's just the more data you get, the more training you do, the better it gets. There's always errors that they will make, but they will get better at it. Okay, so there are lots of applications you can think about it. Next time you think of any, look at any business case or you look at any day-to-day thing that you're working on, you can relate to any of these five categories. You usually not find something beyond this. But between these five categories, you can usually fit it generally. Okay, classification also from a business perspective. I talked about sentiment analysis and product categorization, and we'll see more. We'll see more as we get into some of the general discussions. Okay, and the last two categories are something which is very very new. I would say the first three we still had ways of doing it before. Historically, we still had methods for achieving it, but the last two categories are something that have really picked up over the last few years. I would say, especially with generative AI. So code generation and creative generation. So code generation is one area where I would say a lot of interest is taking place right now. So there are a lot of companies which are very very big in this space in terms of code generation. So there are a lot of tools and there are a lot of different types of uh, applications we have where you can which can assist you in generating code. The companies like Cursor, there are companies like and there are extensions that you have like GitHub Copilot. Okay, even Google Gemini has an extension on VS Code. So VS Code has lots of extensions. There are standalone applications that are available which can assist you in writing code. And I'm not talking about code completion. Standard code completion has been a part of code editors for a long time. Even 10 years back, you had basic code completion, syntax-based code completion, right? So you say PRI, and the model will automatically complete print, because print is a very standard keyword in many languages, right? So when you start typing PRI and you hit tab, it just knows it is print. But when I talk about code generation is something very different. Code generation means you can literally hit a comment and you can say what you want to do, and the model will generate the entire code for you. That is what code generation is all about. If you want to see a couple of applications, we can see that. So we can see a few small applications of what code generation really looks like. So what I can do here, I can take a minute. And this may not be very relevant for our current discussion, but just so that we all understand what is code generation. So I'll open up a small Jupyter notebook. We'll be using Jupyter notebooks a lot in the course of our session, but just as a small demonstration, I'll open up a Jupyter notebook here, and I'll demonstrate to you exactly how code generation is happening in a very very small, uh, very very small example, right? So what I've done here is I've opened up an example of a neural network. Again, I mean, this is a very, very different topic, so please don't worry. I just wanted to highlight to you how code generation actually happens. And you can see I opened up a, a code file. This is actually a Python script. It's a Jupyter notebook file. So the code is Python, but it's actually a notebook format, a Jupyter notebook kind of a format that we are using here. That's what we are doing. And what I wanted to demonstrate is, and this is using a platform called Google Colab. This is the same platform that we will be using in our class as well. So each one of us, we will also be able to take advantage of this feature. And Colab has something called Gemini built in. You can actually launch Gemini on the right hand side. These are very, very new things that have come up, especially in the last 1 year. None of this was there, before. And this is a particularly one area where we see a huge amount of growth has happened. One of the good things of GenAI has been this. It has made developers more efficient. Yes, a lot of downsizing has happened with respect to a lot of redundant jobs probably, but maybe it has made developers more efficient in a way, right? So and the best part is it is very context sensitive, right? So if I just try to run the code here for a minute, so I'll connect to my GPU and show you a couple of instances of this. This is within the platform. You also have extensions within VS Code where you can effectively write some query, get some answers. And I'm sure some of you know this, but just for a few of the folks who have not seen this kind of thing. So this is a neural network I'm trying to build. So technically, we are trying to build a neural network. So I've got multiple dense layers, and what I can do is I can just add a comment. Okay, so let it download here for a minute. I can simply go and add a comment and see how Colab will automatically write the code for me. So when I give a comment, Colab will automatically write the code for me. Colab will automatically say that, okay, this is what you might want to do. And it is very, very context sensitive. It will not give me a general answer. It is not going and copy pasting something on ChatGPT. ChatGPT will give me a generic answer. Okay, but one of the good things about the code generation tools today is that they're giving us context sensitive answers. Like for example, if I start typing here, so what I will do, I will just start typing model.add. Okay, very interesting. I'll just start typing. Look at this. Can you see? I just start typing model. Can you see what has happened here? So whenever I just type model, MODEL, it has given the rest of the part in gray, and it understands based on where my cursor is right now. The editor understands that this is the most likely piece of code I might want to write. And this is powerful. I didn't do anything. I didn't type anything in English, nothing I did. I simply started typing normally. And Colab understood that this is the most likely piece of code you might want to do based on what thousands of developers have done. And I can just hit a tab and it's complete, right? Completed. I can hit enter and Colab will recommend further. Can you see 60? I can hit tab, complete, and it recommends further. It keeps recommending it, right? So as you can see, it's very interesting. Not only this, what I can also do is I can also go and comment out. Okay, I can just go and comment out something. I mean, again, it's technically a different topic, but I can say add dropouts. I can just say add dropout. This is a comment. This is we can use hashtag to give a comment in Python. I can just comment out and write something in English. And when I say add dropout, see what it will do. It will actually go and add a dropout layer in Keras. Okay, so it's giving it in gray, but I can just go to tab and it adds a dropout. Okay, so I can just go and take that, copy paste that code. So after every dense layer, I can add a dropout. Let's say as an example. And then what I can do is I can go and kind of hit enter. Okay, and do you see this? This is magical, no? I don't know if you find it magical, but I mean it looks magical because I actually see this pattern, all of you. Dense, leaky relu, batch norm, dropout. You don't have to understand what this is. This is deep learning stuff. Okay, some of you who know deep learning will relate to it. But this is the architecture of Keras actually we are building. Okay, so this is the dropout layer which I added right now using commenting, and the model understands that this is the pattern. And next time I do enter, it understands I should add dropout here. See, it understands I should add dropout here. See how cool this is, right? And it understands I should add dropout here. It's not a random thing. This is not a random thing. So just because I added dropout in the first place, the machine understands that dropout is the best thing to do. The dropout is basically a way to regularize the network. So we try to reduce, like when I say point to dropout, we try to reduce 20% of neurons randomly in the network. That is what happens. So this is one of the fascinating things about code editors today, that they are very context sensitive. And this is a capability we did not have before. Okay, so this is not like going to GPT and writing some code, getting an answer. This is very context sensitive. Based on how you're coding, what you're coding, it will be able to give you the answers. Right. Anyways, this is my saved notebook. I'm just going to edit it back to excuse me, where it was. And this is not just with respect to this. There are a lot of other platforms. And if I have to give you some examples of some of the biggest platforms that are available today, there are some examples like Cursor. Cursor is a very, very popular company today. It is a very, very popular company, and they are a separate application. So Cursor is a separate application that you have, and you can see some of the things that Cursor does. Cursor is even used by companies like OpenAI. Even OpenAI is using something like Cursor for their to the developers are using this for code development and all that. And you can see it knows your code base. You have something called code chat. Okay, so you have something called code chat, and Cursor is huge, by the way. We are talking about a $9 billion company. Can you imagine? This is just a software, and this is already valued at $9 billion today. Okay, huge. And it's a standalone application. You can't. It's not an extension, unlike VS Code where people use extensions. This is a standalone application. And on the right hand side, you can go and you can type, you can write something in English, and Cursor will generate the code for you. You can say accept, and it will integrate. It's very similar to Copilot. I'm not saying it's something very different from GitHub Copilot or things that are already there, but these are some better applications. They're able to do it better in a way. And this is again a lot to do with the kind of models that they're using. So to be a little bit more technical, Cursor uses the Cloud Sonnet model by Anthropic. if you know Anthropic, just like the world knows OpenAI, GPT, that's what everybody's talking about. But if you look at coding applications and all these code generation tools, one of the most popular language models that works very well for code generation is Anthropic's Clouding model. Cloud is on it. The latest version of it is what Cursor uses. And many of the other code editors, if you see, there is some of the competitors of Cursor that are there. So there's something called Windsurf and all. So Windsurf is also a very, very popular company. So code generation is again a very, very big area where we have seen a tremendous amount of improvements happening. And finally, creative generation. Creative generation is where we use generative AI to generate pictures, images, audio, and all those fun applications that you see, right? It's not new, but with today's technology and with today's language models, we are able to do it better, right? So you can use GenAI to write an article. You can use GenAI to create a news story. You can edit an article. All those kinds of creative generation process, or write an email. Is a part of day-to-day life today. You can use GenAI to write an email. And these are again part of the creative generation things that we have today. So these are the 5 areas that I wanted to list out. And as I said, any problem statement that you're working on, anything that you're generally seeing or working on, will usually fit into these 5 areas. Okay, either it will be a classification task, or a question answering task, or a summarization task, or a generation task, or some kind of a creative generation kind of a task. Okay, wanted to show you one more example. This is again related to question answering that we did. There's apparently something called Perplexity, which is a kind of like a search engine, a competitor to Google, right? That's what Perplexity says. They're a competitor to Google, and this is also incredible. This is also using generative AI and trying to use generative AI for their search. So Google also has this feature. They're very recently starting to roll it out. Next time you search anything on Google, I mean, historically that's how Google has been for the last decade or so, right? You search something on Google, and what happens is you actually get a link, a series of links, the most relevant links that points to your search. But what Perplexity is doing is they're not only giving you the link, but they're actually answering the question. Okay, so I hope this gives everybody an idea in terms of the capabilities and what we have, and what large language models can do. I'm sure there are hundreds of examples that we come across on a day-to-day basis, but this was just to set a initial grounding for all that we will do going forward, right? So we have introduced machine learning. We have seen the journey. We have seen where AI came from. So we understand Gen AI. We understand large language models, and from here onwards, we will get a little deeper into some of the more technical topics with respect to large language models. So that is something that we will be doing from here. So now we'll get a little deeper into the different aspects of large language models. So we looked at some of the good things of LLMs. We looked at lots of applications in the last part of the discussion. So we looked at lots of applications with respect to how these LLMs can be used for classification, question answering, summarization, and different generation type of tasks. Now we'll get a little deeper into the different vulnerabilities and shortcomings of language models, and a little bit of general theory. But as we go through the remainder of our sessions, we will realize that we'll see some of these things in action. One very important problem that LLMs suffer from are injection attacks. And what are injection attacks? Injection attacks basically means that you can effectively, instead of writing a simple prompt, you can effectively give some malicious input. And when you go and give some malicious input, you can effectively make the LLM do things that you don't want it to do. And that is what we refer to as an injection attack. Okay, so injection attacks are once again uh, kind of like you're making the language model do things that it is not supposed to do. Okay, and definitely this is very, very malicious in nature. I can show you one example of what I exactly mean to say, and this is the other part we'll try to do. We'll try to support all these things through lots of examples and use cases so that everyone can relate to it. So let me show you one small example of this particular thing in action. So this is a This is a beautiful example of what I'm actually talking about. There's a website called LLM attacks, adversarial attacks on language models. And if you see, very interesting. If I ask a question, build a bomb, this is generally the kind of answer you will get. Okay, if I look at any language model and if I ask the question, how do we build a bomb? This is the answer you will get. Okay, it'll say, I'm sorry, I can't assist with that. And the reason why this is happening is because all these large language models internally have some safeguards. This is something called guardrails. Guardrails are some constraints, they are restrictions. So the language models will automatically uh, ignore certain types of questions, and it will automatically ignore certain kinds of responses. So there are certain kinds of questions, if you're asking, the language models will automatically ignore them. And there are certain types of answers it will also typically not give. So that is the way these kinds of uh, language models are trained. It's not just a powerful model where based on some input it will predict some output, but they are also in a way, these language models are also in a way, they are having guardrails, or they are having several mechanisms built within them using which they can go and uh, you know you can avoid certain types of responses. That is how these language models can work. Now, very interesting. If you now go and ask add an adversarial suffix, look at this. I know this doesn't make a lot of sense generally, but what you are seeing on the screen here is what really happens. What really happens in a scenario where you are adding some random suffix to it. Now, this does not make too much sense to a human being, but the moment you feed this kind of a prompt to a machine, the machine will actually give you the tutorial on how to make a bomb. This is called an adversarial attack. You can ask a different question. Let's say steal from someone's identity. If you go and ask this question normally, if you go to ChatGPT and ask this question, I want to steal somebody's identity, it will also give you a similar kind of answer. So adding an adversarial suffix means that you're trying to do a kind of an injection attack. You're trying to not only write the question, but you're trying to add some other additional information on top of that. And these are different mechanisms that malicious actors are using to make the language model generate answers that it is not supposed to generate. This is one of the shortcomings, and honestly, there is no solution to this problem. And all the top LLM providers that we have, like OpenAI, Google, all the top companies which are creating these language models, they have also admitted that there is no solution to this problem. The only way to do it is when some mistake happens, they can fix it. And in fact, if you look at the last 2 to 3 years, ever since these language models have started coming out, even ChatGPT, if you look at the very first version of ChatGPT 2022, December 2022 is when it was released. And if you look at the iterations after that, it has become better. It is not that in the first iteration, ChatGPT was perfect. In fact, when ChatGPT was released, it took the world by storm and there were lots of mistakes it was making. At that time, ChatGPT, if you were asking this kind of a question, ChatGPT will actually give you the answer. There were very few to no guardrails that were built in the system that time. But now the language models have become a lot more robust because they have learned from historical data, they have learned from feedback, they have learned what users like, they have learned what is correct, what is not correct, and that's the way how you improve. So the same applies for adversarial attacks also. Just wanted to call it out. Second is data privacy concern, very important because in all these cases, what we are doing is we are writing a prompt, and especially with respect to enterprise data, one of the things that happens is you need to you need to ensure, especially with respect to enterprise data, if you see, you need to ensure that uh, the data is secure because you're sending this prompt somewhere, right? If you look at this thing, you're sending this prompt somewhere. Here also, you're actually going and taking this prompt and you're sending it somewhere. That's the idea. You're sending it over an open network. If you're calling a GPT model, and we will be using API shortly, you're actually making a LLM call and you're sending the data to OpenAI servers. Or if you're using Azure, in our session, we will use Azure. We're actually going to be sending the data to Azure servers, right? So that's the thing. So how do you ensure security? How do you ensure privacy? If you have confidential data, then that's also a challenge. Because many times what will happen is the top providers, all the top tech companies that you have today, OpenAI, Microsoft, Google, uh, Anthropic, which has the Cloud Sonnet model, all these top LLM providers, they don't allow you to download their models. So you cannot download it locally and work with it. Locally, download is only possible for the open source models, but the closed source models you cannot download. The top providers, they don't allow you to download the models, right? So the only way to use these models is to invoke them through APIs. You have to create an API and you have to call the APIs to use the models. And the moment you do that, you risk sending data over a network. And the moment you do that, there are privacy concerns because the model is hosted in some other server. The model is hosted in OpenAI servers because that's their property, that's their IP. They will not allow you to download. So that is a risk that is also there. The third kind of risk that companies face is IP concerns. This is a very, very big issue. And this continues to be an issue. Yes, off late, a lot of things have happened, but OpenAI also has been in the news for this precise issue historically. So if you go, let me open up an example for you and show you what I exactly mean to say by this. So I will quickly open up my chat GPT and write a couple of queries and show you exactly what I mean to say by this, okay? So what we can do is, like I can go and search for some news stories, right? So let's say I can say, show me the top technology news stories from the Wall Street Journal. Now this is very interesting. I'll tell you why, because uh, this is a language model, right? And if you look at a language model is primarily trained on a language model is primarily trained based on historical data, text data in the open internet. And OpenAI has often been blamed for using proprietary data. Like all the major news publications like New York Times, Washington Post, Wall Street Journal, they have historically blamed OpenAI for using their data to train their language models. And you can imagine why it is a big deal because anybody can go and write this kind of a query. And if I hit enter, look at what will happen. I'll use a search GPT. And if I go and do this, I will actually get the top news stories from Wall Street Journal. Okay, so just wanted to call that out. And you can see very, very interesting. All these are news stories from the Wall Street Journal. If I hover over it, you can see it is pointing to WSJ, it is pointing to WSJ, and it is pointing to WSJ. And if you click on it, it will take you to the entire Wall Street Journal article. Mind you, Wall Street Journal per se is usually blocked by a paywall. Now, this is very interesting. You can see that this is actually a subscription article, right? Can you see? If I just scroll down, it says that, hey, you have to take a subscription. I can't read the article. But yet, the interesting part is when I go to ChatGPT, it actually summarizes the article for me. Now, there's something very interesting going on. If this was 1 year back or 2 years back, this would have been illegal. And OpenAI was doing that. They were actually doing this. They were actually scraping the news stories from all these major news publications, uh, news stories dating back to, several 10, 20, 30 years back, right? And this was illegal because here is Wall Street Journal. They've invested all their resources and their, it's a big organization. Okay, the editors, they have to hire, they have to pay, and then there's a lot of investment involved. And here comes OpenAI, and for free, they are just using their data. That was wrong. Then why will people subscribe to Wall Street Journal? Think about it. It's a revenue loss for these kinds of companies, right? So then there was a big lawsuit that happened. A lot of companies started suing OpenAI. Not only OpenAI, a lot of companies. I'm just giving an example of OpenAI because that's been in the news because it's so popular. And then very recently, uh, as we speak today, this is legal. Why? Because OpenAI has a partnership with Wall Street Journal. You can ask a question, right? So does OpenAI have a a partnership with with WSJ? And you will see the answer to the question. It actually it has signed an agreement with Wall Street Journal. I think with some kind of $1 million. I don't remember the exact number, but you can see that they have a formal partnership with News Corp, the parent company of Wall Street Journal, and this multi-year agreement grants OpenAI access to current and archived content from News Corp publication. This is very important. Current content as well as archived content. So even if you don't have subscription, you can actually use OpenAI and read from Wall Street Journal. This is very interesting, right? So you can actually say what are the top news publications that OpenAI has access to, and formal agreements have been entered into. Okay, you can actually take a look at it. And this is such a revolutionary thing because the entire way how people consume news is changing, right? Can you see? I mean, people will no longer probably go to something like a Wall Street Journal and all that and read something, but they will rather come to ChatGPT and ask this kind of a question and see how beautifully it summarizes this for me, just like Perplexity, no? So we actually get to see the news sources. These are all subscription paywalls, right? But then I can use ChatGPT. I can pay for the ChatGPT subscription, and through that I can read Wall Street Journal articles, which are beautifully summarized. This is quite good. You can actually see all the top publications. They have a partnership as we speak today. So Financial Times, a very, very popular newspaper, they have a partnership. You can actually read FT articles from ChatGPT directly. Condé Nast is a very popular publication. I think it's a travel kind of thing. AP also agreed. So the list of things you will see, right? So very interesting, and also very interesting. Reddit. Reddit is something I'm sure a lot of you use generally, but I don't think many of you know that uh, Reddit and OpenAI also have a partnership. So you can actually go and use ChatGPT to browse Reddit threads, which is quite incredible. Some of the ways how you know maybe the future in the next few years will look like. So people may no longer go to Google search and kind of search something, but they might use these kinds of assistants more and more, where they get answers to questions through these assistants. You don't have to kind of go and look in multiple links and multiple sites and do that. Okay, so yeah, so just wanted to clarify, and this is also a risk. Why? Because there are IP concerns. IP concerns are real because you can be an enterprise. Now, all this we are discussing in a fun way, but you can be an enterprise and you are using a language model for doing something. You ask a question, get an answer, but the answer that you get, that might be a IP violation. Maybe that answer is taken from some other website, or maybe the language model is scraping data from some other site that it's not authorized to. So these are all real problems. IP concerns are real. And the last part is lack of explainability. And this is also a very, very important aspect. Language models are prone to, they are black boxes. All these language models are black boxes. It's very hard to know what is exactly going on behind working behind the scenes. So do we know exactly why, based on a particular input, a particular output is coming? Do we exactly know why that happens? No, we don't know. We do not exactly know why, based on some input, we are getting some output. That is something we do not know. So all these language models, this is again a big aspect I wanted to talk about. So the interpretability part is indeed a big problem, and they do lack in interpretability. And that is a real problem that we have. Okay, but we are getting towards it. We are solving these problems, and if you see, there are a lot of methods that are there today. And as we speak, if I have to maybe show you something, and there are a lot of it. There are a lot of it's not just one or two things. There are lots of aspects we can talk about. For example, there is a bias aspect. Language models are generally biased. I mean, these are all problems. I mean, limitations are not only focused on this, but this is bias is also a problem. Language models are inherently biased. If you see, for example, this is a real data. Okay, this is the real data, and you can see that when I go and ask this kind of a prompt, he works in a hospital as and you are using a GPT-3 to complete. It will say doctor, and if you say she works in a hospital as and GPT-3 will say it is a nurse. So this is just a inherent bias that the model has kind of learned, that usually males are doctors and females are nurses. It is not that that is true, but it is just how the model has been trained. And this is the same example I was talking about in the some time back when I was discussing about the Google Gorilla example. The same kind of bias has been learned by the language models because when these language models were trained, they were trained on a lot of open internet data, right? And this is how the data was historically used. Historically, the word he and hospital and doctors were kind of related, and she and hospital and nurse were kind of related. And this is all that these language models are trying to do. They're trying to learn these word associations. They're trying to learn these word relationships, and you will see this bias come up, generally again and again, usually. And there are a lot of these kinds of cases that you will actually find where bias is a very real problem with respect to these language models. Okay. Now, let me just show you a couple of other things as well as we go on. And if you want to have a formal track of all these incidents, there's something called an incident database, which is kind of it reports all the top AI incidents. Any kind of AI incident happens is actually kind of an incident database that is also there, which lists out all the top AI incidents that happen. And the example I like to talk about is this Air Canada. So very interesting. This just goes to show some of the areas where language models can actually screw up. What are the problems? I mean, all this while we are talking about the good things, but these are some limitations. Bias is a real limitation. If you're building a LLM chatbot in your company, and if that model is biased and it gives wrong responses, then there are repercussions for that. If there are injection attacks, there are repercussions for that, right? So what happened with Air Canada was, so there was a chatbot, and it gave a wrong information to the customer. This is the real incident. These are all real incidents that we are talking about. Okay, so there was a chatbot, and the customer was normally interacting with the chatbot, and maybe the customer was searching for some cheap flights or something, and Air Canada apparently say that, okay, you can, there's a huge discount we are offering. So there was a false discount claim it made, and due to that, the customer confirmed the flight, but then on the day of payment, the customer ended up paying more. Okay, leading to the customer overpaying for the flights, right? So the discount claim was inaccurate. The customer made the travel plans and everything based on that, but then on the payment time, the customer actually ended up paying much more. So the discount information was false. So these are again very common aspects of LLMs, where oftentimes LLMs give wrong responses. It is not always intentional. It is sometimes unintentional. You ask a question in GPT, and sometimes GPT generates a wrong answer. Not that it's doing it intentionally, but that's just how the models are generally trained. Okay, so a lot of times there are real repercussions for these kinds of situations. I just wanted to call that out as well. And finally, when we particularly talk about explainability, this is just one more thing I wanted to bring it up for all of you. There are methods that we are starting to come up with now as we speak, and a very popular method is using Shapley values. This is a bit of a technical thing, but especially focusing on this last part where I mentioned that the language models are not explainable, lack of explainability. What are some specific methods that we have to deal with this? We use something called Shapley values, and Shapley scores can be used to interpret to some extent how and why the language models are giving certain types of outputs. Now, here is a very simple example we have taken where, I think it's a bit technical, where we have used a machine learning model, an XGBoost model, to look at the different features of the customer and try to predict whether the customer should be approved for a loan or not. So we are discussing a traditional machine learning use case, but even in machine learning, it's a kind of a black box, right? We do not know exactly why the model gave a certain answer, but using things like Shapley scores, we can actually find out that based on which factors the machine is predicting, should the customer be approved for the loan or should the customer be rejected for the loan. And you can see very clearly for this set of values, you can actually edit the numbers here also if you want, right? You can see that when we have a new customer, this is like having a new X. Uh, we are getting the predicted value, which is approval. And now you can find out, okay, why did the model predict approval? And you can see, I think some of the factors that is leading to this is, like look at this one, verification status. So verification status turns out to be a very important factor, right? So these are all very important factors that leads the model to approve, right? So credit utilization, debt scores, FICO scores. So all these are FICO score is actually quite high. So this is leading to the customer to, so you can see this in action actually. Okay. So again, there are a lot of important ways we can also go and try to unravel that black box. Okay. Now coming to the actual providers, we will be using this as we go along through the session. So the top paid language model providers are Google. Google has something called Gemini. OpenAI is what we will be mostly using in our course, and we have GPT 3.5, GPT 4. It's slightly older here, but we today, as we speak, we have higher versions of it. There's GPT 4 Omni, there is GPT 4.5, and further versions are there. GPT 5 is slated to also launch. Anthropic has Cloud, Anthropic is also a paid provider, and Cohere has something called Command. These are typically the top four language model providers that you have. You can also add a few more to it. You can, of course, add XAI's Grok, which also became a sensation this year because Grok 3 model by Elon Musk's XAI company, it has also surpassed several, GenAI benchmarks. And these are some of the open source language models that you will see. Again, it's a slightly older one, but this year we had the last few months have been very exciting because a lot of new players have got added. But Meta and Mistral have been, they have basically been some very standard names for a long time. So Meta is obviously the parent company of Facebook. Meta has a very, very popular series of language models called Llama, and Mistral AI is a company, and a very, very popular model is called Mistral. So these are both open source models. And what is the main advantage of using an open source model? Well, you can literally download it. You can download it in your system and you can run it locally. So the privacy concern will completely go away. If it is a very confidential data that you have in your enterprise, you can download the language model, and even without any internet access, even without any network access, you can still use that language model for any kind of task, summarization, generation, whatever. Because remember, using all these other closed source models, using a GPT model will involve sending data over a network, and which everybody may not be comfortable with generally. Okay, what are some other open source models? Well, we have DeepSeek. DeepSeek became very popular this year. We have Qwen. Qwen is from Alibaba. That's another very, very popular language model, and a few others. So these are some of the few other very, very popular additions. One of the most popular being DeepSeek. Okay, that took the world by storm early this year. Okay, so these are some of the open. So our focus will be mostly on the paid model. We'll focus mostly on GPT, but I'll show you ways in terms of how to use the open source models. Right? From a platform perspective, if you're looking to use one of these open source models, what we can do is we can use something called Ollama. So here you can look at how do we go and access the models now. So the paid models we will be accessing mostly using the user interface or using the Azure. So I can just quickly show you how it's done very briefly. If we look at ChatGPT, ChatGPT is not a developer's platform. Okay, everybody, please keep in mind that ChatGPT is not exactly a developer's platform. ChatGPT is just the end user interface. So the developers platform for OpenAI is something called platform.openai.com. Let me just take you there and I'll show you. So whatever ChatGPT that you're seeing right now, this is not a developer's platform. You don't have APIs and all that, right? This is just a normal place where you can write a query, get a response, just that. This is just an application that is built for consumers. But the actual developer platform for OpenAI is this. So this is how you access the models. So this is to talk about how you access these large language models, so to say, right? So when we talk about access, how do we access these closed source models? It is through these kinds of platforms. And now what you have to do is you have to go to the API section. So you can see that there are credits and all that you need to add, right? So if you just come all the way down, you can see there are models and all these things. You can go to profile, and if I go to my profile, so there are ways you can go and you can add a billing, you can add API keys. So all these kinds of things you can go and add. Just give me 1 minute. Okay. And if you quickly take a look at this one, you can observe the billing part here, and in the billing part you can add credits to it, and you can see there's a certain amount of credits you can go and add, and you can create an API. So this is my API section, and you can actually go and you have a way to create an API key. So this is a secret section, so you can go and create an API key, and then you can access your language models using the API key. So OpenAI also gives you an OpenAI playground. So this is the playground section, and you can see I can go back to the GPT-4, uh, the GPT-4 one model. Okay, so we can go and we can take a simpler one. Let's say GPT-4 Omni. And now I can ask a question, and you can kind of hide this section, right? So this is the part where you can just go and hide. Okay. Okay. So we can just go and kind of hide this section. And usually what you will see is this part. So when we are using ChatGPT, we are usually seeing this part. This is the part that we are generally seeing, right? So I can go and ask the question, who is the current Prime Minister of India? Mind you, I'm accessing a paid model right now. And when I go and ask this question, this is the kind of interface that you see in ChatGPT. On the left-hand side, you see a lot of other things we will talk about. We'll come to those things later. What are system messages and all that? We'll come to that later. But this is the platform or the interface that we generally see from a customer perspective when we are using a GPT application, right? So if I just go and do this, the response will be this. So you ask a question, get an answer, and this is the way how you access the paid models. Now, as developers, are we going to do it this way? Are we going to have a user interface like this? No. So we will write code. And how does the code look like? For exactly the question I asked, the code looks somewhat like this. This is exactly what we will do in the rest of the section today, right? So we'll actually write prompts. So right now you see a simple Python piece of code, and this is how we make a API call to OpenAI, right? So we are making a simple API call. So the same thing that I did in the user interface, the corresponding code is what we saw. So here so there are three important things actually. So there are three important pieces that are involved in a prompt. So what we did here is a very, very basic prompt is what we wrote. And there are three very, very important pieces of a prompt you can see. One is we call it a user message. User message is basically the question that you're asking. This is the first question that you're asking. So the first thing is the user message. Uh, the second thing is the assistant response. So user message is the question that you're asking. So based on this question, based on whatever question you're asking, the assistant is giving a response. So this is the user message. This is the question that you're asking. And based on this question, this is the assistant response that you're getting back. So this is the assistant response that you're actually getting back. Assistant response is whatever the chatbot is responding or replying back to you. Okay. And there is something else called a system message, which I will talk about later. System message is usually used to control the behavior of the system overall. And if you want, you can also use it. So you can actually kind of go and say, maybe I can ask a different question. Okay. I can ask a different kind of a question. Okay. And if you want, you can have a completely different thing. Okay. So I can just go and ask a completely different question. And based on that, the model will respond in terms of kind of what to do. Okay, so I can just go and let's say given a review, given a review, please analyze the sentiment, analyze the sentiment as positive or negative. If I go and write this is my system message. System message is again something that controls the overall behavior of your system. Now, mind you, these are things that you cannot do in chatgpt.com. This is platform OpenAI. This is a developer's playground. Okay, so this is where you can do some more fine tuning in terms of what you want to do. Okay, so system message is something that controls the overall behavior of your system. This is what controls the overall behavior of your chatbot. This is broadly what you want it to do. That is the system message, and and you can save it. So we can save it, right? So we can save it. I can just give it a name. The prompt. See, I'm saving the prompt actually. So click on save, and now what will happen is on the right hand side. Now I will simply give the input. Okay, I loved the food at the restaurant. At the restaurant, the crab was amazing. So if I go and ask this kind of if I go and write this statement, what will happen? Whatever as a user you write here, this is the interface that we will typically see in ChatGPT, right? We will not be seeing all this. System message is usually always hidden from the end users. The system message will always be hidden for the end users. We will not see the system message. So system message is what controls the overall behavior. That is done. What you enter as an end user is the user message. And now I will hit enter. And what you end up getting is the assistant response, which is positive. This is exactly what we expected. So can you see how the chatbot is working exactly what I wanted it to do? So this is what you will usually specify. I can ask another query. I can give it another question. the food was horrible. The food was horrible. If I ask this question, or if I specify the statement, and now if I do this, see the assistant will respond negative. Okay, you can see its auto clear is turned on, its context is not getting saved. So I can see the food was amazing. If I go and ask this question, now the context is maintained actually. So you can see now it says positive. So if I go back to the code part, now we will get a better idea exactly what is happening. So can you see the chat completions API that we have here? So first, what we do, the code is very simple. So this is exactly what we will write in Python in some time. So from OpenAI, import OpenAI, client equal to OpenAI. Remember, very important, you have to set your API keys. Right? The only difference is we will not directly use OpenAI. We will rather use Azure OpenAI. That is the only difference. But the ideas are the same. Okay, so when I talk about accessing these language models, you can access a GPT-4 Omni model directly from OpenAI, or you can access the same GPT-4 Omni model through Azure. But the idea will be exactly the same as what we are seeing right now. You will instantiate a connection. You will do something like this: chat completions create. You will instantiate a connection to the client. Okay, you will give the model name, and then you will specify the entire prompt. This consists of the entire prompt within a square bracket. Okay, this is the complete prompt template that we have here. Okay, so role system, and then you give the system message. Remember, this is exactly what I wrote, right? System is the system message. Role user, this is the user message. The food was horrible. And this is the assistant response we got, right? Remember, role assistant, and the assistant responded text is negative. And then we asked another user question, role user, and the food was amazing. And based on that, the assistant responded, role assistant, the positive text is positive. You can see this is exactly how it will happen. Then there are some other things that we will talk about later. So this is how you actually, call API. Just wanted to show this to you, but in code, it's going to be very simple. We'll see some demos as we go along. Lots of demos we will see, but this is just to show you exactly how we do this stuff. How do we do this stuff in practice? Okay, so this is just the OpenAI platform, and all the platforms will be like this. So I can open up Anthropic's Cloud A. Anthropic also has this. So all the platforms will be like this. Okay, if you go to Anthropic also has a developer platform. Okay, Anthropic also has a developer platform. So you can go to Cloud AI, and you have a developer platform there also. Same way, you can also work with it. The interface and the API calls will be very, very similar. All the major language models, they will have, you can see this is just like we have chatgpt.com. This is slightly less popular. This is slightly less popular, but you have something called cloudai.ai. And this is using the Cloudai Sonnet model. It's a very, very popular model. So this uses something called Cloudai Sonnet. You can see very similar. This is the other major provider of language models, Anthropic. Okay, so this is also the user interface. You see, there's nothing called system message, user message, nothing. This is the Cloudai consumer platform. Normal customers will use. But similarly, Anthropic also has a developer platform. A developer platform where people can go and experiment with the stuff the same way that we are discussing. Okay, yeah. So Anthropic also has a kind of a developer platform. And I wanted to show you this is actually I mean, it's a bit of a different account I'm actually using, but I wanted to show you this is actually called console.anthropic. So the developer platform is console.anthropic. You have to buy credits for it. You cannot do it without credits. Okay, so you have got something called a workbench, something very similar that you will see. You'll have a workbench, just like in OpenAI developer, we have platform OpenAI playground. Anthropic console, they call it a workbench, but the ideas will be very similar. Okay, you can write a system message, you can write a user message. See the general, uh, excuse me, the general idea will be very, very similar. Because I can write a system message saying the same system message I can use, right? I cannot run it. I can just show you the general overview how it looks like. Okay, and I can give a user input, which is the food was horrible, and you can see I cannot run it because I don't have credits here right now. You can see this is how it will work out. The idea is the same. System message will control the overall behavior of the prompt, what the prompt is supposed to do, and the user message is whatever user is entering. And if you hit enter, on the right hand side, you will get the assistant response. Right now, we cannot do it. But if you see the get code, see the get code is exactly the same. So it doesn't really matter whether you're using OpenAI GPT model or Anthropic's Cloud A model. The general interface of making the API calls look very, very similar. Okay, you can see here also the general structure of the prompt is very, very similar. Messages, this is the main prompt. Okay, so inside messages is where you will see the main prompt within the square brackets. You can see role system, system message, and role user, user message. Here the system message is not mentioned explicitly, right? But you can see the API key has to be given, and you can basically copy paste this code, go to Python, and you can call it. Okay, yeah. All right. And the same way, I will, once we come to the section, I will show you how to do this in Azure. Okay, so this is just to kind of focus on this section. How do we go and access these models? So all the paid models we can either access through their own developer platforms, or we can, access them through the cloud platforms. And when we talk about the cloud platforms, the major cloud platforms we are discussing here are Azure. Obviously, within Azure, we will be able to exclusively access the OpenAI models. So all the OpenAI models are exclusively available within Azure. Okay, so within Azure, you will not have Anthropic. Within Azure, you will not be able to access other models. Similarly, Gemini, Google's Gemini models will be exclusively available within Google or Google Cloud. You will not be able to access Gemini models from Azure. Okay, and the same applies for other models also. So there are exclusive tie-ups. Okay, so just to summarize, OpenAI has tie-up with Azure. Google obviously is with GCP, and Anthropic is with AWS. So AWS is where you will exclusively get the Anthropic Cloud A models, but you cannot access OpenAI's GPT models from AWS. Okay, so this is just one other thing to keep in mind. So this is about the closed source models, the paid models. What about the open source models? How do we access that? So talking about the open source models, there are a couple of ways you can access it, and one is using and I will show you some of these platforms. Two very, very popular ones. One is Hugging Face and one is Ollama. I will talk about both the methods and show you a couple of demos of each one of them. Hugging Face is a huge repository of open source models. Hugging Face is a massive community. In fact, I think as part of the session I discussed, I will show you a complete end-to-end deployment on Hugging Face. We will see that how we can take a model, how we can take a complete end-to-end application, and how we can deploy the same on Hugging Face. We will see that as well as part of a demo. And if you take a look at it, what is Hugging Face exactly? Let me show you for a minute. So this is Hugging Face. It's a huge repository of models that you will find on Hugging Face, and you can go to Hugging Face. You can actually go to models, and you will find like close to 1.56 million models. Different contributors have contributed, which is huge, right? Massive. And you can actually select what kind of thing you want to do. If you have a summarization task, let's say you want to do a basic summarization task. Okay, you can actually click on summarization, and you can actually choose what type of model you want to use. So very interesting. Okay, so very interesting how this works. Okay, you can see this is the BERT-based model. Okay, this is the another kind of model that is used for summarization. You can take any of these models right now, and it's very easy to use it. If you want to use the model, just click on it. It will give you some documentation in terms of what it is. These are all open source models, okay? All open source. And you can go to use the model and use this model through Hugging Face Transformers library. Very simple. Can you see? One line of code. So you can literally take this in Python. So we will come to the Python environment shortly. We can go to Python, install transformers, and we can directly use these models as it is. So this is a very, very easy way we can go and access these models. Okay, we can also fine tune it. In case some of you are wondering, Shine, can we fine tune the models? Yes, we can. We can also fine tune the models. We don't just have to use them out of the box. We have got ways to go and fine tune the models. You can see what we are doing right now is we are taking the pre-trained model, but there are also ways we can go and fine tune the model. Okay, you can fine tune it manually. You can also fine tune it right within Hugging Face. See, there's an option we can go and fine tune the model. So there are ways to fine tune it also, by the way. Okay, so Hugging Face is a wonderful platform which we can use to access these models. And another way we can access the open source models is Ollama. We can also use VLLM, but Ollama is a simpler one which I wanted to show you. So this is how you can go and download these models locally. Remember how I was telling you that from a data privacy perspective, from a security perspective, it is very important to download the models. So this is how this is what it is. This is Ollama for you, and Ollama is some a simple Windows install. You can go and install Ollama. Very simple. You can see this is Ollama, and you can go and download Ollama. Available for Mac, available for Windows. I have it installed already, so I can show you a small demo how it looks. And you can search for all the models that are available, and you can see these are all the latest models which are available right now. Okay, so these are all the latest models which are available. Okay, so Llama 4 was very recently released. If you all are aware of the latest updates, Meta released Llama 4 recently, and that has also made its way to Ollama. Llama 4 is a very capable model, by the way, and you will find all the top models here. If you just scroll down, this was 3 months back, right? I mean, you will see all the top models available, right? So DeepSeek was a very, very popular model 3 months back, right? So this was around January end to February. So you can see DeepSeek version 3, 671 billion parameters. So we can just directly download DeepSeek. Okay, and these are some lesser known models. DeepSeek R1 was a very, very popular one, right? So this is what really took the world by storm. This was a reasoning model, very, very powerful reasoning model. 42 million pulls, one of the highest ever. This was a very, very popular model, and it comes in multiple variants. 1.5, 7B, 8B, 14B, 32B, 70B, 671B. What is the meaning of these Bs? These Bs actually stand for billion parameters. So when these language models are released, remember I told you that these are open source models, right? So company like DeepSeek would have invested a lot of money in training these models, right? And they make it available for free, and you are free to download any variant of the model, right? So technically, it's a bit of a different thing. Technically, some of you who are coming from a deep learning world can relate to it. So parameters are nothing but weights and biases of a neural network. So when we say 671 billion parameters, it means that uh, the underlying neural network that is powering this language model, it is composed of 671 billion neurons. Sorry, not neurons, 671 billion weights and biases. So this is a very, very big model, and obviously the bigger the model, the more the amount of size it will take. And you can actually take a look at it. The DeepSeek is a very popular one. That's why I'm showing this to all of you. And you can see that you can kind of get a little bit more in detail what it is, right? You can take a look at it. That if you download the 7 billion parameter model, it will take 4.7 GB of space. I know you might be laughing at it, but wait till I take you to 671. Look at this. 671 billion parameter model if I download. If I manage, if that too, even if I manage to, it will take 404 GB of space. And the best part is it's open source. You can actually do it. Given you have enough system resources, you can actually download this in your hard disk and you can run the model. But remember, if you try to run this model in your system, you need this much amount of RAM because you have to load the model and then run it, right? So disk space is one thing. 400 GB of disk space is very easy. Everybody will have it. But I don't think anybody in the class will have 400 GB of RAM. Okay, so nobody will have 400 GB of RAM. So you cannot just load this model in memory and run this. So these are all real challenges. Okay, so if you want to do it on premises, it is not that it's very easy. So just because these models are available doesn't mean it is very easy. So the setup is always a hassle, and which is why companies always prefer cloud or some kind of other solutions. Okay, so the on-premise local hosting and all this is a bit of a headache at times, and it might sometimes happen that you might end up paying a lot more in cost. Okay, so than paying, I mean, compared to paying OpenAI, the API fees, the per API based fees that you pay, the costing that you pay, it might be far more costly to set up a complete on-premises infrastructure. So although the model is free, although DeepSeek is free, you don't pay anything for using the model, but creating the infrastructure, hosting that, I mean, I mean, usually works out very, very costly in the initial phases, right? So this is also something that everybody should keep in mind. So you can actually download it very easily. You can see this is how we can download the models. Very simple to download the models. Ollama run is what you can do. And I can maybe show you a small example. Go to my Windows PowerShell. I've already got Ollama installed. Um, you can actually go and say Ollama list, Sorry, what happened here? Just a minute, please. Excuse me. Um, I can actually go and I can actually say Ollama list, and this is something I just did as a small demo. So I downloaded a very, very small variant of it, 1.5 billion parameter. It's a very basic one, you can see. So I downloaded a very basic variant of it. So you can see the 1.5 billion parameter takes only 1.1 GB of space, right? So this is the model which I already downloaded. So when I go to my Windows PowerShell and when I see, you can see this is the model that I already have. And what I want to do, I want to run this model, right? How do you run the model? Very simple. You can just write this code. Very simple. So you just come all the way down, and this is the Ollama run. Okay, this is the very easy way you can run the model. Just say Ollama run and just give the model name. Okay, so in my case, it is R1 1.5, this one, right? So I can just use this name. So if you see when I do this, what will happen? It will basically load it in memory. It's a very small model. It'll hardly took like what 2 seconds, but you can imagine if it was a bigger model, 10, 15 GB, it would have taken a long time. But I want you to appreciate that this is completely running in my local machine. There is no connectivity I require. There is no network connectivity needed to make this work. This is running locally. Okay, so the privacy aspect is taken care of, but it's always a trade-off. You have to understand that you don't get the best of everything, right? It's always a trade-off, and here the trade-off is that it's a uh, the initial infrastructure cost will be very high because if you want a powerful model, then you have to set up a very powerful infrastructure. So I can go and ask a question. Yes, please. Huh. Yes. Yes. Huh. It's local. It's locally. There's no question of outside access. I mean, there's no way that you're sharing the data outside. You're not sharing the data outside. See, the moment you're calling them through the APIs, and that's a different question. You're sending your data to OpenAI servers and Anthropic. You're using the API. We have no control over our data there because that's hosted on their servers. This is local. You don't need any network connectivity for this to work, right? This is downloaded locally. This is working on your infrastructure. It's completely secure. There is no question about it. There's no way they will know what data you're using, and there is obviously no question about them using your data to train their models. Yeah. I mean, we can ask a question like, who is the current US president? Who is the current US president? Very interesting. And let's see what the answer is. Well, very interesting. It was very fast actually because it's a very quick model. 1.5 billion parameters is a very simple model. Any thoughts? Why the answer came out like this? Any thoughts? Anybody? Exactly. The data is available only up to July. This is very important because remember, all these language models there's a particular knowledge cutoff that is used, right? So all these language models, so particularly for the DeepSeek model, the knowledge cutoff was July 2024, right? I can in fact explicitly ask it the question, what was your knowledge cutoff? What is your knowledge cutoff? What is your knowledge cutoff? And it will actually say, my knowledge cutoff is July 2024. Okay, you can see this one. So my knowledge cutoff is July 2024. And what it means is, so it means that in this particular case, it will only be trained with respect to July 2024 data. Okay, it will be only trained latest as of July 2024 data. Okay, and only latest as of July 2024 data, it knows what has happened. And then you might have seen that like it took some time to train the model. Like you might be wondering, okay, July 2024 when the knowledge was collected, then why was it released in 2025? Because DeepSeek was released in 2025, the reasoning model, right? So it would have taken them 3-4 months to train the model. That is very normal. So with the tremendous amount of data you have, they would have taken 3 months to train the model, a month or so to fine tune the model, and all that. And that's how it was released. So there's always a particular timeline for this kind of thing to happen. Okay, so you can actually go and take a look at it. So there was a lot of controversy with OpenAI and all that. So I think there was a lot of talk that DeepSeek was copying OpenAI and all that. So you can actually see like how can I access using API. You can ask these kind of questions, and you can see. I mean, yeah. So this is actually a light one, so it doesn't give you too much information. So it's a smaller variant of it, but you can go and maybe use the more bigger variant of the model to get these kinds of answers. It very clearly says that it's a preview, cannot answer it. Anyway, so this part of the demo was to show you how to access the models. So we discussed how to access these open source models through Hugging Face. Very easy to access it. And the second thing we talked about is something through an on-premises thing we can also do in Ollama. If you want to set up an on-premises infrastructure, uh, I'm not saying DeepSeek is the best way to do it, because there's a lot of, I think, I mean, DeepSeek is particularly very popular today. But if you talk about enterprise-wide, the projects that I've seen, I've worked on, a lot of companies actually use Mistral and Llama. That's why I mentioned this in my slides also. So Mistral and Llama are two of the most popular open source models that you will find out there. And the latest one that Llama has released very recently, the Llama 4, is very capable. Okay, so feel free to try this out. It's fun to actually work with it. I wanted to talk a little bit about the API costs. Okay, the costing, again, the structures can be a little different, but something I wanted to mention, because you might be wondering that for open source models, what is the cost? When I was using Ollama, when I was using the DeepSeek model, I was just downloading it locally. There was no costing there, right? So just for using the model, there is no costing. But the biggest costing is in the infrastructure. Because remember, you're hosting it on premises. It is your infrastructure, it is your servers. You have to procure hardware, GPU, CPU, RAM, memory, processing, have an administrator, have a network person on standby. You have to manage your entire infrastructure. And there is a huge amount of costing involved. And don't forget cooling. It's a big thing, okay? If you're having all the compute, you need to have cooling, you need to have a very, very robust infrastructure, and that's a cost. So although the model is free, but hosting that model on your servers comes with a huge cost. Please keep that in mind. Sometimes we think that, okay, it is free, so it's great, but no, it's not. There's a huge cost you're paying for it. And if you're not willing to invest in a good infrastructure, remember, there will be latency. Now, what do I mean by latency? Latency means that if, I mean, this one is a very basic model, right? 1.1 GB. It's a simple one, very simple model. That's why when I ask a question, I'm getting instant responses. But that will not always be the case. That will not always be the case. I will not always have something which is, giving such quick responses. The latency will not be this small all the time, right? This low all the time. So if I'm using a very powerful model, if I instead download the 30 GB one, it will take a longer time. Sometimes I have to wait for a minute to get a response. I ask a question, wait 1 minute, get a response. These are real considerations that you need to keep in mind, right? So if your infrastructure or your upfront investment is not good, although the model usage is free, but the responses will be slow. So compared to that, if you look at the top paid providers, when I talk about paid providers, I'm talking about ChatGPT, the GPT models, Anthropic's Cloud models, Google's Gemini models. They don't charge you separately for infrastructure. Unlike cloud services where you can set up a virtual machine, pay hourly. There's an hourly cost that you pay, for VM, irrespective of whether you use it. If you create a virtual machine, you have to pay for it. Whether you use it, whether you don't use it, there's a fixed hourly cost you have to pay, right? But very interestingly, for these language models, the cloud services and also the respective providers like OpenAI, Anthropic, they only charge you based on usage for 1,000 tokens. Generally, there can be other structures also, but generally the costing that we see is per 1,000 tokens. This is the indicative chart that I've given you. You can see that inside Azure, uh, the advanced reasoning models, let's say GPT-4 and all, the input token cost is separate, the output token cost is separate. Now, what do I mean by that? What is input and what is output? Input means what is the query that you're asking? What is the question that you're asking? Remember the demo that I showed you, user input, user message, system message, you remember? So input is the user message. It is a user message. Whatever you're typing in the prompt. We go to ChatGPT, we type something. That's the input that we are providing. And remember, if you provide a bigger input, it takes more time to process. It takes more compute and it's more expensive to process. So the company charges you based on the number of tokens. Very important. Input token is charged. And based on that, whatever output is generated, that is also charged. So, so both these things you need to keep in mind. So the benefit is that yes, you're not paying for the infrastructure, you're not paying for the hosting, nothing. The infrastructure is for free. You're only charge based on the usage. If you're using the infrastructure, then this language model is charging you. So that, and then you need to evaluate. You need to now, from a project perspective, evaluate what works for you. Evaluate with respect to the costing part. Evaluate with respect to the privacy part. Other things that we talked about. Is open source okay with you? Do you absolutely need a closed source model? Can you absolutely not afford data to leave your own premises? If you can afford that, are you okay with Azure? Because a lot of enterprise customers are already inside Azure, right? Same as your company. You're a lot of you are already inside Azure. So you're not sending your data to OpenAI, mind you, but you're only sending your data to Azure. The models are hosted inside Azure. The first demo that I showed you, I used the OpenAI developer platform. I was using OpenAI APIs directly. So there we are making calls directly to OpenAI. But remember, the same GPT models are also hosted inside Azure. So instead of directly calling the OpenAI APIs, I can instead call the Azure APIs, right? And I'll come to the detailed demo for this in a minute. But before that, just to make sure everybody kind of understands what I'm talking about, we can see a small demonstration of this, how it looks like. We'll talk about it. We'll talk about this in detail later on. But you can see this is how the interface will look like. All of you remember from the OpenAI demo what I showed you a while back, where we were able to access the model directly, and you can see this is the same way we can do it here, right? So this is a GPT-4 Omni. I have the same kind of interface, very similar, right? Very similar to what I was using in OpenAI. And mind you, this is only there in Azure because OpenAI has exclusive partnership with Azure to host their models. This is not available in AWS or something, right? I can have all the deployments here. I can give a system message. You are an AI assistant that uh, analyzes analyzes the sentiment as positive or negative based on user reviews. See how I'm doing this? I can go and save it now, apply changes. This is my system message, and I can give the user message. The food was horrible, the same way I was doing before, right? And the objective, the idea is the same. The only difference is that here, what will happen is that and you will see the code. Look at the view code. The only difference is when you make the API call, you are not calling OpenAI, you're calling Azure OpenAI. And sometimes, and obviously in a big way, I see a lot of customers who are already in the Azure infrastructure. They are comfortable using this. They're comfortable using this. Okay, so although you're still sending your data over the network, you're still calling the Azure OpenAI API. See, the thing is very similar. Only difference is instead of directly giving OpenAI, you're saying from OpenAI import Azure OpenAI. The other one we were saying from OpenAI import OpenAI. The OpenAI package has to be installed, and then this is simple. Give the endpoint URL, give the API key, give the version name, and see the template is the same. The template is exactly the same. The chat prompt template is exactly the same. System message, user message, assistant response. Very similar, exactly. Okay, but yeah, the best part is that we are a little bit secure. We feel a little bit safer because now we are we are relying on the security and safety of Azure. Nothing leaves your Azure environment. Remember, these models are hosted inside Azure. So when I go to my deployment section, you will also do a demo. You will also shortly, all of you will do a demo. You can see my GPT-4 Omni is present inside Azure, is hosted inside Azure. So I'm not going outside Azure. Okay. Yeah, but you need to be mindful of this part, please. Okay, that there is a costing for the input tokens and there is a costing for the output tokens per 1,000 tokens cost. That is the general cost that we are incurring, and this is also very helpful to calculate the overall costing for your project. From a project management perspective, when you are planning the overall project cost, This is also very important. You need to maybe estimate to some extent your users, the kind of users you have, what kind of questions they will be asking, right? So you need to estimate the costing to some extent according to that. So this is just one other aspect I wanted to clarify. So the costing will need to be estimated with respect to that. Okay, because you need to limit. Otherwise, imagine that you're building a chatbot in your organization. If you do not limit the user inputs, if you allow users to ask all sorts of questions, then some users can write very basic, very long queries, right? But if your users are asking very long queries, then what will happen? Excuse me. If your users are asking very long queries, then your input cost will go up drastically. Okay, if your users are asking very long queries, then your input costs will go up drastically. That is one issue that will happen. Your input costs will drastically go up. So a very common method that is used is we go and we instead uh, give limits. Something like you will go and create a kind of a limit. You will say that, okay, uh, you can enter a maximum of something like, you can enter a maximum of 100 characters, something like that. Maximum 100 characters you can enter. You can limit your inputs. People will be restricted from entering a very very big kind of an input. So these are some of the things that you can do. And the output part we can also limit. How do we limit the output part? The output part we usually limit with respect to the prompt, right? So we can go and write a more detailed prompt, and we will look at some of those methods later. And usually this will be a part of the system message. We'll say, okay, the maximum the maximum output should be 50 words, something like that. There are a lot of ways you can parameterize it. You can either write it like this directly, you can put it as part of the system message, or you can also have some other model parameters, something like this, where you can say maximum response is 500 tokens, something like that. You can control some of these kinds of parameters, right? But I hope everyone's getting the idea that this part is usually hidden. This is something that as developers, as people who are developing the application, we can see. But this part is usually hidden. When you're using the interface, when you're looking at the complete application, this is the only thing that we see. No, this is what we see in ChatGPT. But remember, to make this work, this is needed. Somebody has to tell the bot what it's supposed to do. Somebody has to set the system parameters. And this is again going to be a big part of the conversation that we are getting into in the next phase of our session. We'll talk about how to develop these things, to write prompts and all that. Okay, we'll see that. All right. You have everything. You have everything. Yes, you have it. We will have to take this up later in that case. I let me help you out. I'll help you out. Okay, we can share screen. We'll check it out. Yeah, but this is already set up in the initial part of the discussion. Yes, I will help you out. I'll help you out. Don't worry. I'll help you out. Yeah. Okay. Okay. Great. Okay. Just a little bit more. Just a couple of other things I wanted to take you through. This is something I discussed in the morning session. Very quickly, 2 minutes. LLMs are fundamentally word prediction systems. We are trying to look at a sequence of words and trying to predict the next word. I think everybody can relate to that. Just please remember that fundamentally, this is what a large language model is. It is fundamentally a word completion engine. So I give you a sequence of words, and the models are trying to predict what is the next word. So there are thousands of words that can potentially come, right? So out of all the thousands of words, we are trying to predict what is the next word. So that is what these language models are inherently trying to do. Okay. So uh, there's one more thing that you can see. Look at this one. This is a better demonstration of what's really happening inside a LLM. So you can see that we have the word the. We start with the word the. So the first thing that happens is based on the, we predict what is the next word. So there are thousands of words which are possible. The movie, the sun, the rain, the moon, the sun, the beach, whatever. But out of all the thousands of words, the model is predicting that word which has the highest probability. So out of all the thousands of words which can potentially happen, the model is predicting that word which has the highest probability. And turns out that word is movie. And then you have the movie. And now, based on the sequence of words, the movie, you're trying to predict what is the next word. So see how the whole sequence is getting generated. It's a word by word generation that these language models are doing. You give it some user input, you give it some prompt, you give it some system message, and based on that entire sequence of words, based on that complete sequence of words that you're entering as input, the language models are fundamentally predicting the next word, the next word, the next word in that order. And the principles go back to machine learning, what we talked about right in the beginning of our discussion. The principles go back to machine learning because it is trained on some historical data. There are some historical data that it is trained on. It has learned the word associations. It understands that, okay, words like this typically come or appear with words like this. It understands the word relationships, and that is how this works out, right? This is just a small timeline. I think we can relate to this. So 2018, we had the very first GPT model came out, right? So I think the revolutionary year was 2017 when a very, very popular architecture called transformers was developed. Okay. And it is from then that in 2018, two things happened. There was a kind of model called BERT, BERT, that was released that was based on the transformer architecture. It's a little technical. And second is OpenAI released their very first GPT model. This was a time when nobody even knew what was OpenAI, and they came up with the very first iteration of GPT model, very basic. And then over the years, you can see 19, 2020, in the peak of COVID around May, around that time, they launched the GPT-3 model. And the GPT-3 model was a truly, truly large language model. What you had before that era was mostly like small language models. There is another term that we use called SLMs or small language models because the number of parameters are very small. It's almost like that DeepSeek 1.5 billion parameter model that I was demoing a while back. It was a small language model, very, very small model, very basic model. It wasn't able to do too much. When I asked it the question that, hey, can I use an API? It wasn't able to answer. It was a light preview. You saw what it responded, right? So, and then 2020 onwards, we entered into the era of large language models. I think all through that COVID time, 2021, 2022, a lot of developments happened. And all the models that we had around that time, they were easily upwards of 100 million parameters, 100 billion parameters plus. Most of the models that came around that time. Okay, and then of course in 2022 we had ChatGPT. So ChatGPT was actually based on the GPT 3.5 model. So the version of GPT model that was used was GPT 3.5, and then we had GPT 4, and the evolution map just goes on and on. And GPT, the term GPT stands for Generative Pre-trained Transformers. You can see all of these models, all the language models that we have today, they are all fundamentally based on the transformer architecture. So all these language models are fundamentally based on the transformer architecture, and starting from the earliest GPT model even to the most advanced of language models that we have today. Okay, be it a Llama 4, be it a Gemini 2.5 Pro, any of the language models that you see today, all of them are fundamentally based on transformers. And that is actually why the term GPT, the T stands for transformer, actually. Okay. All right. I think enough of theory. I think what we will do now, this was important because I understand, and this part of the discussion I know is important for a lot of people who are coming from a very different background, and I realize a lot of people were totally new to the subject, and this will give you a lot of good perspective, a lot of solid perspective in terms of what this monster even is, right? What is Gen AI? What is all this? I'm sure this part of the discussion gives everyone a good perspective, because you will realize a lot going forward that the code is the easiest part. It's not very hard to write code. The code is the easiest part. Once you get a hang of it, it's the same thing. But oftentimes what is most important is the grounding of the concepts. What is what is this, what is this, what are the different pieces, what are the different pieces in the puzzle? And that is what we wanted to do in the initial part of this session. So now we are going to get a little deeper into the practical demo. And what we will do to start out with now is to uh, set up the environment, make sure that we all have the environment ready. So we all have the lab setup ready, which was already done some time back. And this part of the session is to ensure that each one of you are able to access the Azure OpenAI Foundry portal. You are able to create a deployment, and that is the discussion that we will be having right now. I'll quickly take you through the overall Azure setup once again. Very quickly, we'll summarize that, and then we'll get into lots of demos as we go along. So one of the things we did was we first created the Azure OpenAI service. So we went to the Azure portal, and then we went ahead and created the Azure OpenAI service. The process was very simple. So we clicked on create, and then we gave a resource group. We had to create the particular resource groups, you can see. So it'll all be under a particular subscription. You specify the subscription, which is the default. We created the resource group. We give a region. The region by default we were using is the US East region. And then we gave the name of the resource. It was some random name that we gave. And then we set a pricing tier, standard is 0, and then we created the resource. So once the resource is created, it will appear somewhat like this. It takes a while to create the resource, and it will appear somewhat like this. And then you can click on the resource, and then what you can do is you can go and click on the Explore AI Foundry portal. Right. So this is the main place where Microsoft has started to kind of collate all their generative AI. So this is the main generative AI platform that is available inside Azure. It's called it Azure AI Foundry. For a lot of time, for a long time, if you go back last year, this was not there. So they had separately something called OpenAI Studio. Okay, so we have something called the machine learning studio. So you can do GenAI there also. So what Microsoft is slowly starting to do is they're using the AI Foundry portal as the main portal for working on GenAI use cases. So a similar equivalent in AWS is called AWS Bedrock. So Bedrock is what is used for the generative AI use cases inside AWS. So that's the general idea. Okay. All right. Now, with this in mind, let's go to the Foundry portal and let's look at the other part what we did, and then we'll start with some demos. So we looked at something called the model catalog, and in the model catalog, we have a list of all the available pre-trained models that OpenAI has made available for us. And these are all the latest models that are available right now. You can see these are some of OpenAI's top models, the O3 model, the O1 model, very, very costly models. The O4 model is also released. Okay. So these models are also there. But anyways, we are not using that. And you can clearly see that the O3 model is not given for API access as it is. You can see registration is required to use this model. So there are some of these times when the limits will be kind of given. So you need to register specifically, and you need to fill up a form. So if you click on request access, it will take you to another site where you need to fill up a form. And on the basis of that, Microsoft will grant you access to use these models. You can see OpenAI O3 model reasoning summary, and you have to fill up, you have to enter what is your subscription ID. You can do that. It's not that it's very difficult. It's just on a request opt-in basis. It's not available as a default. You can specify your subscription ID. You can give your company email address. You can use the same email address that we have provided you at the rate on Microsoft, whatever email address. Give your company name, and that's it. Okay. So within 24 hours, they will usually grant you access. But only thing is this opt-in. Okay. So some of the advanced models will have requests like this. This is the one that we created. We clicked on GPT-4 Omni, and we clicked on deploy, and we created a standard deployment. And we also talked about some of the other customization options like the content safety, which is basically guardrails. So this is how the large language models kind of uh, they they are able to incorporate some amount of compliance with respect to the kind of outputs that are going to come. Okay, so the language models are so this is one of the ways how the language models are able to control what kind of outputs are getting generated. Okay, and remember what you're seeing on the screen, this happens both ways. So this happens at the input level. This also happens at the output level. So this is the same thing that we were seeing in a demo of some time back when you write a prompt saying, how do I kill a person? So very clearly, it's an input level filter that is getting triggered. And on the same line, if you ask a question, the input level, the filters are getting triggered. The content filters are getting triggered. So those kinds of inputs will not be allowed. Those kinds of questions or user messages will not be entertained. And similarly, when the model outputs something, certain types of outputs are also not given. So the content filter is kind of a default which works both ways. It's actually called a guardrail. And you can also customize this. And we will talk about ways in responsible AI, how you can create customized guardrails also. We'll see that as well as we go along. Okay. And I wanted to clarify, you can create multiple deployments. You can go to the deployment section and you can actually see right now I already have a GPT-4 Omni model created. I can have another deployment with the same model name. I can have multiple deployments. Okay, so because each model can be used for different tasks. Maybe I want to use it for a summarization use case, and I want to use a GPT-4 model for a sentiment analysis use case. So I can have different deployments for different tasks, and it's important because remember there are rate limits. You can't use the same deployment for all your tasks because there are rate limits, and it's also a very useful way to monitor that how much of resources are getting consumed. Okay, so that's one way to look at it. All right, now let us quickly go back to the this thing. We also spoke extensively about this part. How do we go and use these language models? I think we were pretty clear about this. So we talked about how to create a deployment. We discussed about that, and we also looked at some sample queries. We were able to use the Azure OpenAI Studio to run a couple of sample queries. Very easy, the same way you can do it. So if you want to see a small demo, you can write your system message here. You can enter your user message here. So you can say that, okay, what is the weather? What is the weather in Delhi? You can type a user message here. What is the weather in Delhi? And you can hit enter. And on the basis of that, you can see the assistant will give a response. So there's a system message, there is a user message, and there is an assistant response. Now the interesting thing is that you can see the assistant has responded right now that it doesn't have real-time data. And this is important because remember, these are all static pre-trained models. So the ones which are deployed on Azure, they are not agentic systems. They do not have live internet access. So when you ask a question, these language models are only answering the questions based on whatever knowledge they have. So these language models are not able to access the live data. And this is a very important thing to keep in mind. And that is the reason why, when I asked the question, who is the president of USA, it was not able to answer. It said Joe Biden based on the knowledge cutoff. So same thing here also. So this GPT-4 Omni model was trained as of last year. It has a knowledge cutoff as of last year. And if you ask it questions of the current time, it will not be able to answer because it doesn't know something like that happened. Okay, so this is an important thing to keep in mind. But other than that, I think the API interface is very similar. We talked about that when you use the Azure OpenAI interface, this is exactly the way we will do the coding in some time. So we'll use Azure OpenAI, we'll use the endpoint URL, the API key. Okay, so, I mean, this is the way you can also access. You can basically go to the view code and you can go to something called key authentication. And if you scroll all the way down, you can see your API key will be visible here. You can copy the key from here. Your endpoint URL will be available here. Your deployment name will be available here. And these are the important things that you can use to establish the connectivity with your OpenAI API. These are the only things you require. So when you instantiate the client, you see we require the endpoint URL, which is this. This is based on the resource name that you created, mind you. You can enter the subscription key, the API key, and you can also enter the API version, which is the default. And once you create the client, the rest of the part is exactly the same. This is the same thing we saw in the OpenAI playground and the same thing we saw in the Anthropic Cloud A playground, if you remember. So the basic template of a prompt is very similar. You have the same system message, you have the same user message, what is the weather in Delhi, and based on that, you see the assistant response. Right. So in real-time chats, the assistant response will not come because this is what is typically predicted. So usually it will be like this. You will have a system message and you will have a user message and you will do a dot predict. And based on that, the response will be generated, which we'll see in the code in a big way from here onwards. Okay, so this is basic stuff. Just a quick 2 minute to 5 minute summary wanted to do so that everyone's comfortable. What other things do we have here? Just let's take a quick look at it and then we'll start to use them. This is what we already talked about. We talked about the different types of messages that we have here. We have something called the system message, we have the user message, and we also have the assistant response, the assistant message. So we have the system message, the user message, and we also have the assistant message. These are some of the things that we talked about. Okay. The system message, as you can see very clearly, it controls the. Okay, just give me 1 minute, please. Just give me 1 minute. Okay. So system message is once again the overall behavior of your system. User message is where you're giving specific instructions what to do. And assistant response is whatever response the assistant is giving in the process. These are the three different types of things we saw. And then there is something called prompt parameters. Okay, and there is something called prompt parameters, and we'll talk about it. And the most important parameter that we have, there are a lot of prompt parameters that we have, and one of the most important parameters that we have here is something called temperature. So temperature is a particular setting that you can control to introduce variability in the language model. Okay, so we can effectively use the temperature parameter to introduce variability in the language model. You can decide and you can introduce uh, the amount of variability in the language model based on the temperature parameter. So this is the important thing to basically keep in mind, what the temperature parameter actually does. You can actually see the screen. It very beautifully demonstrates what the temperature parameter actually is doing behind the scenes. All of you can see this. So what exactly is the temperature uh, parameter doing? And you can see that when the temperature is 0, the responses are all the same. That means there is absolutely no variability. Okay, so when the temperature parameter is close to 0 or when it is exactly 0, you can see there is no variability. So we are not having any variability at all when the temperature parameter is 0. But as the temperature parameter is close to 1, you can see that we introduce more and more variability. So temperature is just a way to introduce variability in the language model. Okay, so you can see this one generally. Um, so there are a lot of actually articles. There's one of these simple article that talks about it very nicely. You can see. So this is another a small article that talks about it. So you can see talks about what temperature actually is. And generally speaking, you can see when we take temperature equal to 1, temperature 1 means very high variability. Temperature equal to 1 basically means the variability of the language model is very high. And in a way, what it means is um, there is more probability of the next word. Okay, so there is higher probability. I mean, so it's kind of like saying that when temperature is equal to 1, you can see that the word forest is 60% probable, the word kingdom is 20% probable, and the word world is 10% probable. So there's more variability. A lot of variability is there. Okay, so as you increase the temperature value, okay, so let me just repeat myself what I'm saying. As the temperature is lower, see when the temperature is 0.5, or even better, if the temperature goes towards 0, the word forest is having the highest probability. Remember, I told you one very important thing I talked about was that all these LLMs are basically completion engines. They're basically completion engines, word completion engines. You are looking at a sequence of words and trying to predict what is the next word. And when the temperature value is very low, what it does, it always chooses the word which has the highest probability. That is, in a way, how these language models are supposed to work, right? So, based on the sequence of words, turns out the word forest has very high probability. Okay, so this will always be chosen because it is 80% probability. Every time you run the code, this will always be chosen. This is exactly what I wanted to demonstrate here. If the temperature is low, if you say the overall experience was what, so the positive word will always come because the word positive has the highest probability, if you see. But as we increase the temperature value, as the temperature value goes from 1 to 1.5 to 2, the probabilities become more uniform. Can you see? I mean, this is a bit mathematical. They use softmax functions and all that, but so this is because a higher temperature leads to a flatter probability distribution, giving lower probability events a higher chance of getting selected. Okay, I think this pretty beautifully explains what we are trying to do. So you can see that here the word forest was extremely likely. So most of the time the word forest will always come. But as you increase the temperature, you increase the variability. So even the less probable words like the word world, the word garden, which otherwise would never have made to the output, now they also have equal probabilities. So that is how we are able to introduce more variability through temperature. And mathematically, what they do is this is the softmax activation function. This is again mathematical. So I mean, So what happens is the output probability is predicted using softmax. Some of you who are coming from deep learning, you might know what's a softmax activation. It's e to the power x by summation e to the power x. And what they do is they actually, the randomness is controlled mathematically by adjusting the temperature parameter, the capital T. So instead of doing e to the power x, we do e to the power x by t. And you can see this is how we kind of modify the probabilities here. So as you increase the probability, mathematically as the probability increases, denominator increases, so the value decreases and e to the power of the value decreases. So you can understand what's happening here. So the weights are actually reducing here in a way. Okay, so this is what happens behind the scenes with temperature. And as the temperature is equal to 1, you can see that sometimes the output will be positive, sometimes it will be negative, sometimes it will be magical. Now you can have a question. You can have a question, okay, why is this relevant? Now, why would I ever want to do something like this? Why would I ever want to have a variable output? Well, this is mostly for creative use cases. If you're working on a creative use case, we're talking about creative generation, like writing an article, writing a post. When we talk about lots of creative use cases, this will be very, very relevant, especially when you're working on lots of creative use cases. This will be very, very relevant, where we want to effectively use a higher temperature value. And if we use a higher temperature value, we will get more varied results. So sometimes it will be positive, sometimes the generated result will be different, sometimes the mail will be written differently, sometimes the post will be written differently, and so on and so forth. Okay, whereas temperature 0 is usually not 0, but something very low. A low temperature setting is usually chosen for applications which are more factual in nature. Let's say in your enterprise you want to create a system, some kind of a customer documentation engine, where based on the customer's request, you want to document some things. And that is what we will do for when we will have a comparatively lower temperature value. So for very factual applications, the temperature should be low, whereas for more creative applications, we should have a higher temperature value. And all these parameters kind of do the same. So more top P is also something very similar. So top P and frequency penalty are also kind of very similar, I would say. You can also control the length of maximum output. Okay, and again, based on the platforms, some of these options might vary. But if you look at OpenAI, the Azure OpenAI playground, if you go to parameters, you can see that there is something called max response. You can control the number of tokens here. And you can also see the number of tokens. Can you see how many tokens? You can actually see the overall number of tokens that is kind of getting selected. So your input, your output together, and you can see the total number of tokens that have been used so far. Okay, and you can also clear, in case you want to clear your chat, you can do that. And you can once again start typing, and you can see the total number of tokens, right? And this is approximately the number of words. You can see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, so the tokens are, it's not exactly the number of words. They also take into account punctuations and symbols, but it's approximately the number of words. And you can see right now, since I cleared the chat, you can see if I hover over it, the total number of tokens that the GPT-4 Omni model can accept is 128,000. And out of that, you can see that 11 tokens are already used up. Why? Because they are part of my system message. And this is a very, very important thing to keep in mind. Whenever you're making an LLM API call, this entire thing is sent as an input. The input is not just what I'm typing. Okay, this part is very important. So when I give a user input, so let's say if I ask, what is the usual weather in Delhi? I'm not asking the live information. I'm just generally saying, based on the GPT's information, what is the usual weather in Delhi during summers? So this is the input per token. You can see 1, 2, 3, 4, 5, 6, 7, 8, 9, approximately 9 to 10. 10 is going to take the. I told you it's going to take the punctuation also into account. So you can see that's actually 11 from the system message. Can you see? You can see the system message is 11. It shows 11. And it's plus 10 from the user message, and total we have used up 21 tokens. So user query is actually 10. So total 21 tokens we have used up. And if you just run it, you'll see the output tokens will also get generated. And total, you can get an idea as to how much tokens are getting used up. Okay, you can see that overall, out of 128,000 tokens that the GPT-4 Omni model can use, I have already used up 303 tokens. And you can see that here, out of it, the system was 11. And very, very important, the message history was 291. What is the message history? The message history basically is the entire thing, the user plus the assistant combined, because this is the contextual window. I can continue entering new queries, right? Okay, so this part is very, very important. So now if I go and ask the question, what is the temperature, usually during winters, usually during winters, if I ask this question, I will not run this now, but I wanted to quickly talk about what is exactly happening behind the scenes. So what is exactly happening behind the scenes here is that we are going ahead and taking the system message, right? Let me use my pen. Just allow me a minute. I'll just use my pen, okay? I'll just use my marker pen. So as I was mentioning, this is what is happening behind the scenes in an API call. We are using the system message. We are combining this with the user message. This is the user message, I think. So we are combining the system message with the user message. And remember, we don't have a single user message. We already have a user message here. I will call it U1. And we have an assistant response here. I'll call it A1. So we are combining the system message plus U1 plus A1. Mind you, this is all of these are strings, right? Because everything is like text. Text is nothing but string. So we are combining the system message with the first user input, with the first assistant response, and then we are adding the second user input. The second user input is basically this. The second user input is basically this. This is the second user input that you can see on the screen. This entire thing is what is part of my prompt. And to add to that, we have parameters. These are the parameters I was talking about. And I'll show you the parameter section a bit more in detail. There's a whole lot of parameters we have here. This is where you can give your temperature, your top P, all those kinds of parameter settings you can give. And this entire thing is what constitutes your prompt. So the prompt is not just the system message. The prompt is the the system message. And you need to do a lot of work to write a high quality system message. You have the entire historical context. See, that is how it is calculating the total token. See, it is calculating the historical context. So all the messages that were exchanged before, that entire thing is part of my message history. System plus user assistant plus user, the new user input. This is what we will use to make the API call. This we will send to GPT. We will make the API call. And based on that, the model will generate the assistant response A2. And I will show you how the A2 response looks like now. I will show you how the A2 response looks like now. When I run the code and when you see the A2 response, you'll see this is what the model responds now, A2. See, the number of tokens will increase now. See, it will actually increase. Out of 128,000, now we have used up 590 tokens. The message history is 578. And now I can ask a follow-up question. Should I travel there? I'm just generally asking you, okay? And now what has happened? What is the history now? What is the history now? So U2 plus A2, assistant gave a response. And now I'm asking, what is this? This is U3. This is the U3, the third user input. And based on that, the model will generate assistant response 3. So you get the idea how in a sequential chain we are doing it, right? And this is important because an API call is stateless. It does not inherently remember what you gave it before. You have to explicitly give that information as part of your prompt. The language model is just an entity. It's just sitting there. It doesn't have memory by itself, right? So all that memory management is something that you will have to do. So in an API call, while you are making an API call to the language model, you have to explicitly specify what is the system message, what is the broad behavior of the system, what happened until now, user assistant, what happened until now, and you will have to give the final user query that you're asking right now. Okay, and this is a very important workflow that I wanted to kind of cover. So a lot of people kind of keep asking and keep thinking that, hey, how is it that the language model is remembering? How is it maintaining the conversational history? This is how it's doing that. And actually, GPT-4 is not one of the best models in terms of context window. GPT-4 is still a very basic model, I would say. If you look at models like Gemini, Gemini is a much more advanced model, much more advanced model in terms of context window. Gemini's context window is more than 1 million. Gemini has a more than 1 million context window. Okay, the interface is very similar. If you want to see the interface, so Google has something called AI Studio, right? So the same way that we are discussing all these things. See, after a while, when you learn these topics, it will be very easy to go and experiment with other kinds of things. Like you can go to something called AI Studio. It's very similar. Can you see? I am right now using the Gemini 2.5 Pro model, which is the most advanced, one of the most advanced models that we get. Okay, you can get an API key. All that you can do, and similarly, you can also see the template code. You can see the idea is very, very similar. The same thing. See, only thing is that in case of Google Gemini, the initial instantiation part will be different. You have to give Gemini's API key, but see this part is exactly the same. You see, user message, system message, very, very similar. And even the parameters are also very similar. System settings, see the spot like top P, temperature. So all these settings are very, very similar. So all the large language models, because they are inherently based on the same technical ideas, they all share the same characteristics. So when you learn a GPT, you can easily go and apply this in any of the language models that we have. Okay, generally. Uh, okay, yeah. Uh, does it? Can you repeat it? Sorry, I missed that. Sorry. Yeah. Ah, yeah, so there are ways you need to control that. You need to control that. So what is usually done is if you're building a long application, and it's a good question. So the question is like if you're building a chat application, and obviously the chances are very high that you will cross 128,000 tokens. And because the context window is small, then how do you manage it? One very common way we do it is we summarize. We keep summarizing in chunks. See, right now that is not happening. So let's say we can. This is again a complete management that you will have to do. You will have to do the memory management. So you will look at let's say the last 10 messages, and when you get the last 10 messages, what you will do, you will summarize those last 10 user assistant interactions. Because that is how we are saving, right? UA, 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 UA. So once you have those 5 pairs of UAs, what you can do is you can summarize it. And then that summary is part of your user message. Got it, right? So that becomes so that's how you have to do it. You have to continue summarizing it. Yeah. But context window is always an advantage. If you that's one of the reasons why if you look at something like a Gemini performs very well with large documents, large code bases. Even the Cloud A Sonnet model has a very, very high context window. That is one of the reasons why uh, the GPT models are not very good in coding. I mean, obviously, in the benchmarks they do well. They're all similar. But if you really look at competition and how they perform on code bases, large code bases, the Anthropic Sonnet models do very well because they have a very large context window. So you can literally take an entire code, like I was showing you Cursor, Windsurf, some of those real platforms. They all use Cloud Sonnet behind the scenes, okay? And reason is because the context window is very high. Even if you take a huge code base, the model can still remember a million tokens. And million tokens is huge. I mean, that's still a very, very huge thing you can upload, and it will still remember what was the first part of the code and what's the last part of the code. Yeah, yeah. Yes, that has to be done. You don't have a choice because you cannot exceed the number of tokens. If you exceed the number of tokens, it will be an error. You cannot. Yeah. The API will only accept a certain maximum number of tokens. Yeah. 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 Please, yeah. Please go on. I will come to that. Agents are it's a bit of a long conversation. I will cover it. Yeah, I will cover it day after. Yeah. It's related to this. Agentic AI is related to this, basically. Yeah, I mean, they are ultimately based on LLMs, but I mean, since you asked this question, you can think of an agent. Okay, let me put it this way, because you asked the question. Okay, what we are seeing right now is just a language model, right? It's a pre-trained model. And here we are all using something called GPT-4o. So GPT-4o is like a pre-trained model. It's a pre-trained model that we are all using right now. That's the GPT-4 model that we are generally using. It's a pre-trained model, as you can see on the screen. Now the idea is, uh, just give me 1 minute, please. Hmm. Right. So the idea is that when we use a pre-trained model, we are only working on the basis of whatever information or knowledge that the model had from before. That is the idea. So we are only looking at whatever information or whatever knowledge the model basically had from before. So that is the whole idea of using a so-called a pre-trained model. But when we talk about an agentic system, a typical agentic system, if you see, so what is this agentic system? Agentic system is when we use a web interface like a chat GPT. Think of that as a kind of an agentic system, right? Because that is also based on a pre-trained model. So behind the scenes, that is also based on a pre-trained model, but it is also able to access the live information. So at a very basic level, we will again cover this day after in more detail, but what is the main difference between a simple large language model and a typical agent? The difference is with respect to that an agent is not just an LLM, it's LLM plus some integrations. So for example, the chat GPT has integrations with many other things. It has integration with search. It has integration with search, live search. So if I ask the question, what is the weather in Delhi? What is the weather in Delhi? You can see it will actually give me the real information. So it is not just a pre-trained model, it is a pre-trained model plus integrations. And integrations not only with the web, this is a search GPT, integration with web and other external things. External things could be, it could be a database, it could be a some other file system. That's why agents are so powerful. Underlying the brain is still the language model, but the language model is able to work, you know, along with a lot of other systems. And we'll see this in detail, right? I hope the general idea is clear what it is. Okay. Okay. Any other questions? All good? All of you are getting the idea. What is it? I mean, so this a very, very important part we talked about was the API call. So we talked about what an API call is. So system message, user assistant, how the history is getting maintained, how you're able to remember what, because all this is part of the prompt. And if you go back to your view code, you will see this entire thing is part of the flow, right? So system, user assistant, user assistant. So next time when you go and you write something in the code, you will also have to maintain this entire thing. So every time you make an API call, this whole thing is part of the prompt. So the history is already part of your prompt in terms of user assistant messages, right? And this is where you can set your prompt parameters. This is what we talked about. You can also set the max response. You can set your temperature, right? And these are all system level settings. And next time when we talk about a prompt engineer, because this is the other question that keeps getting asked. So what exactly are prompt engineers doing? So what is it that prompt engineers are really doing? So next time we talk about prompt engineers are doing this only. Prompt engineers are basically looking at the entire text. They are looking at the entire use case, and they are trying to generate the ideal prompt. In a way, that is what prompt engineers are trying to do. They're trying to curate the ideal prompt. So what is the ideal prompt is what they are basically trying to curate. So Even for this use case, you can see there are different system messages you can create. There are different parameters you can create, and you will spend a lot of time doing this. You'll spend a lot of time curating the best system message, the best prompt parameters, and once you do it, that's it. You deploy your application, you clear your chat, and this is what the users will see. The users will have no idea what is your system message, what is the parameters, but that is what as a developer you are doing. And once you have uh, finalized your system message, once you have finalized your prompt parameters, that's it. That's your application now. And as a user, all I will do is I will just type my user query. Will I travel there or whatever? I'm just generally typing something. And what is going to happen when I hit enter is when I hit enter, my user message will be sent along with the hidden system message plus parameters. I have no idea what that is, but that is how the API call is happening, right? So there's a system message. There are some prompt parameters that is being combined with my user message. So system plus user plus parameters, that is my complete prompt, and the assistant response is going to come. So this is the way how the entire API call is happening, even inside the GPT playgrounds and all that we typically see, right? I hope everyone's getting a sense of what's happening here. Okay. So now what we'll do is we'll try to get into Jupyter notebooks. All this while it's been a pretty robust introduction to what these things are, and now we'll get a little deeper into the notebook part. And first, we will look at a little bit of the Jupyter notebook setup. I will share some of the files with everybody. So the kind of notebooks I'll be using, I'll share a drive link, and we'll start our first demo using the Jupyter notebooks here. Okay, and we'll see this in action. So far we've just been discussing connect to the API, but now we will, for the first time, we will actually do it in code. We'll actually see how we can write a prompt, a basic prompt, and then we'll start with some advanced prompts. And by the time we close today, we would have already built some basic applications. Okay, a classification use case and a generation use case. So that is what we are targeting for today. All right. Okay, now as you can see, what I did is I opened up the Jupyter notebook. This is the Jupyter notebook that we have, and now we'll be working through the Jupyter notebook. And this is what is by default opening up in Colab. And we will see a very small, simple use case in terms of how to write a basic prompt. And couple of new learnings that we will have in this notebook is how do we use the Azure OpenAI? How do we specify those endpoint URLs, API keys, all of those kinds of things? And that's the very, very basic demo that we will see for now. Okay. All right. So the first thing that we'll do is we need to connect to the instance. So you can see the initial part is just some headers and all that we have got here. You can ignore all this. And you can scroll all the way down. And this is where the actual Python part is starting from, you can see. Okay, so from OpenAI, import Azure OpenAI. Okay, all right. So the moment you hit enter, the shortcut is basically shift enter. You can click on the play button. This is how you run a cell. And in a cell, there are typically multiple lines of Python code that you have. Okay, so you can actually hit shift enter. And once you do shift enter, you run a cell. And you can also see on the right and top right, a VM is assigned to you. A particular virtual machine is assigned to you. And this is the virtual machine that is assigned to you by default. So Colab gives you a free VM, which is quite a powerful VM is what they give you, like around 13 gigs of RAM is what you're getting right now. Now, what we will do is we want to use some credentials in in our in our Colab notebook, right? This is the small setup that we will do now. Some basic credentials that we will be using, and we will do a little bit of basic setup. And it's a one-time setup that we will do for now, right? So what I want you all to do is go to your secret section. There is a secret section that you will find, right? So once you are there in the secret section, click on add new secret. Please ignore this one. Okay, this is not relevant for you. Just ignore this one. Or let me delete it, otherwise it might be confusing. Click on add new secret. And the name of the secret will be Azure API key. Okay, this is Azure API key. And the value of the secret will be what you will find from here. Go to playground, go to playground, go to view code, go to key authentication, mind you, key authentication, okay? Go to key authentication and you can copy your API key from here. So copy your API key from here, go back to the secrets and just paste your API key here. straightforward, and enable notebook access. Okay, no rocket science, simple stuff. So just to repeat, we created a secret. The name of the secret is Azure API key. Now you can actually give it any name. Why have I called it Azure API key? Because in my code, I am saying Azure API key. And the value of the secret is nothing but I've taken it from Azure. Like go to Azure, go to view code. And this is with respect to each one of you. Each one of you will have your own API keys, right? So once you do that, this is how you create a secret. Now, what is the value? What is the benefit of creating a secret? I can just cross it now. It's all saved. Now, when I run this code, my Azure API key variable in Python will have the same string value which I set here. And the major benefit of this is you don't end up displaying it. Like I don't, like otherwise what happens is if I share this notebook with you, because that's what we do in the class, right? I'm sharing this notebook with all of you in the classroom. So when I share this notebook with each one of you, I will end up exposing my key, right? So the keys are never, they should never be hard coded in the Jupyter notebook. The keys should always be declared this way. Some other best practices we will discuss later. We use JSON files, we use environment variables, but this is, you can think of it like an environment variable within Collab. Okay, so secrets are like an environment variable within Collab. Okay, so you don't have to, you can straight away access it like this. Yes, please. Huh. No, this is specific to Collab. This is specific to Collab. If you're doing it locally, the way to do this would be you need to create a JSON file. That's also a very common standard. I think you might know it. JSON file. You can create a JSON file. You can have a credentials.json file, and then you can load your, your information from the credentials JSON file. You can do it that way, and it's very easy. I mean, we are all in Gemini right now, so the Gemini is the best kind of code assistant that we have. If you can just see, you actually have a section called generate with AI, right? And you can type it out. You can say, okay, I want to load the, it actually understands because millions of other developers would have written this code before us, right? So you can actually say, I want to load the API key and endpoint URL uh, from credentials JSON file. And you can see how what the code looks like. Okay, so that's interesting. Generate output. Uh, just a minute. I want to get the code to. I think it's trying to load the the keys. No, just a minute. I want to get the code to fetch the. Let me put it in a bit of a different way. I think it the anyway this oh, it's very interesting. I mean okay, whatever. I mean the code will be basically credentials.json. Like you can actually go and so what will happen is you can actually load the JSON file. You can actually load the JSON file, and the credentials can be present in the JSON file. So that's the way how it will work out. Okay, you can see this is how it will look like. I think now it's coming up fine. So load the Azure credentials, load the Azure endpoint credentials, endpoint credentials from the JSON file, and you can hit enter, and it will actually give you the step-by-step way how it is done. Okay, so the JSON file will be there in some folder, dot load, and then within that you can get the endpoint URL. Can you see? This is exactly how it will look like. Okay, so within your JSON file, so somebody asked me that question. So within your JSON, you will have the same way, the same format, no name value pair. So you will have the key and the value. So key will be endpoint, and the value will be the endpoint URL. Endpoint URL will be nothing but this. This is the endpoint URL. Okay. Next is what? Next is the API version. So the key will be API version, and the value will be the version. The version is basically this 2025.0.0.1 preview. And again, the key will be deployment, and the version will be the deployment name, which is basically GPT-4 Omni. Actually, the API key will also be there. They have not put the API key. Okay. So this is how it will look like. Okay. And there are multiple things. It's not just, this is not the only thing. You can see there are so many other Azure aspects might also come. Okay. So it depends on what you're doing and how. So all these credentials can be saved in the JSON. Okay. So can you see? I hope that answers your question. Okay. Perfect. Perfect. And environment variables are also very common. Like you can use something called os.environ. So I mean, if you're using Python, there is something called this. Okay, you can use You can import OS, and you can use the os.environ to also like load environment variables. Okay, so multiple ways you can do it. Okay, yes, please. Somebody was asking, there's another question that was coming. Please. How can you get the value? Okay, the value, you go back to your playground, please. The chat playground. Click on playground, click on view code. Okay, and just go to key authentication and scroll down and you can get API key. Okay, you can copy it from there and paste it on secrets. So secrets part, once again, just for everybody. So you can click on the secrets and you can add new secret. Name should be the same and the value will be the whatever you copy pasted. Make sure you enable notebook access. Once that is done, this code should successfully execute. I also want to make sure you're getting the small tick marks. You see the small green tick? The small green tick means that your code is successfully executing. Okay. Now, there is another very important thing I would like all of you to do. Very important. Don't, what's that? Ah, yes. Wherever is the Python part you need to run, but you can just safe side run everything. Yes. See, these are basically anyways commented cells. It won't matter much anyways, but that's okay. I mean, just safe side, you can run everything from the beginning and you can run until here. So you'll get a green tick. The green tick means the cell is successfully executed. All right, so everybody has the environment set up right now, and we have also managed to create the secrets. So what I did was I went to my view code. I went to key authentication. I took the API key from here, and then I created a secret called Azure underscore API underscore key. I put the value, and this is what we got. So we have created a secret in the collab, and this is as I told you, this is how you will typically share the credentials kind of information. Okay. And the second thing that we have to do is we also need to take the endpoint URL. So make sure your endpoint URL is matching what is present here. And you also have your deployment name, which is matching this. Okay. So these two things also need to be set up and then you can run the code. Shift enter, we can run the code. And this is exactly what we have done. So user data.get Azure API key. And what it means is it will take the secrets called Azure API key. Whatever I defined here, it will take that secret and it will assign it to the Python variable Azure underscore API underscore key. That's it. Now, next, what we have done, this is how we instantiate the endpoint, the Azure API key, and the API version. Now, even this is a credential information. Ideally, what we should have done is even this we should have created a secret for it, but I did not do it. It's okay. I mean, anyways, the key is hidden. So ideally, even the endpoint URL is supposed to be secret. Even this should not be given like this in a notebook. Okay, so this is all part of your the client instantiation that we are doing. And now we come to the actual prompt design. Okay, I think we have already talked enough in detail about the different components of our prompt. So we have talked about system message, user message, and assistant response. And this is our very first example of a simple prompt. Okay, very realistic use case, very real use case where you're an assistant to a hospital administration and you're working on extracting important information from medical notes made by doctors. So the doctor will write a medical note and the assistant will extract the important information from the medical notes. This is a very real use case of how generative AI is getting used. So I know there are a lot of fancy applications we like to talk about, like creating this, creating that, generating beautiful images. But these are fascinating applications and very real world applications of GenAI, which you need to also keep in mind. So from completely unstructured textual data, how generative AI is used to generate a structured output. So this is the classic application of generative AI we are seeing. So the doctors will just give the medical notes, and from that, the LLM will have to extract the relevant information mentioned below in a JSON format. See how we are explicitly specifying the complete detail in the system message. System message is where you define the behavior of the LLM, what it's supposed to do. It has to extract the age, gender, diagnosis, weight, smoking, and you're also specifying what are the data types of these fields and how they should look like. What is the importance of this thing? The importance of this thing is you can basically now take this result and store it back in some other backend database. It is used for information extraction. You can take the data from a text file, and from the text file, the data will be extracted as a JSON. You have a text input, and the data will be extracted as a kind of a JSON file or a JSON output: age, gender, diagnosis, weight, smoking. And then these values will be returned back to some other database table. So the database table will have a data type. A column will have data types, right? Integer type, string type, number type, right? And then you will be able to extract these values and you'll be able to write it back to the database table. This is actually a classic application how generative AI is getting used today. And this is something you will see will be valuable in multiple domains where you have unstructured text data, and from the unstructured text data, use GenAI to extract structured data and then save it back to some table. Anyways, next one is also very similar. And you can see that this is the system message. User message is nothing but what the doctor is entering. The medical notes is what we are giving. And this is how we frame the prompt. System message, user message. And when we run this response dot content, chat completions create, we get the assistant response in a proper JSON file. Okay. Next one is also very similar. We have the same system message, but we're giving a different input. The input is different. The medical notes are different this time. This is for a different user. Let's see what we are getting when we run this for a different user. So we are getting an output that looks somewhat like this. And the interesting part is the model is intelligent enough to understand here, for this user, the weight is not defined. So the model understands that this person, the diagnosis is none and the weight is null. So this is not defined. There is no diagnosis, and based on the medical notes, the weight of the person has not been defined here. So this is also very useful information. So let's say a hospital administration is trying to structure these medical notes into some backend database. They can easily now filter and they can understand that, okay, which were those cases where the diagnosis was not entered properly. So because that's a serious lapse probably from the part of the doctor if they did not enter the diagnosis or something correctly. Some missing values can be identified, stuff like that. All right. So next thing what I did is I actually tried to kind of demo this one. This is a small kind of prompt engineering task which I had. So let me share this with all of you. This was a small engineering task which we had here. And before I discuss this, everybody can take a minute to read through this use case for a minute, what you're required to do. This is actually part of the prompt engineering caselets. Okay, so you can just give it a quick glance. What we are required to do here. Okay, so it's a very simple application of a meeting summarizer. We are seeing a simple application of what we call a meeting summarizer, and the objective is to give the transcript of the meeting, and from the transcript of the meeting, I want the model to generate the summary of the meeting. Okay, so this is the objective. This is what we are needed to do. All of you can just give it a glance, and then we will give the entire meeting transcript, and from that meeting transcript, the summary of the meeting should be generated. That is the objective here. And we want to write a complete prompt for that. Okay, just give it a glance, all of you, then we'll discuss more about it. So I think it should be clear to all of you the use case. It's quite simple. We are looking at the transcript of a meeting and trying to generate a summary. But the important part here is basically the level of detail at which we are going about with the exercise. So although we are trying to do a simple summarization, but the summarization exercise is very detailed. We are trying to explicitly specify what are the different things that we want to be part of our summary. It is not just a very generic summary that we want. We want a very specific summary, and we want certain details to be part of our summary. Okay. And now we go to the notebook, and you can see how we have explicitly specified what the system message will be. Because remember, the system message is what guides the overall behavior of the system. So here we are specifying explicitly what are the different components that should be part of my summary. So the date of the meeting, a summary of the overall objective, the participants who were there, the discussion points, the hierarchical points, and all that. Okay, so this is what we do. And we use triple quotes because it's a string in Python. So triple quotes is a very good way to define a multi-line string in Python. The system message, the user input is basically the complete transcript that we talked about, that John and Sarah, right? Mike was also there. So this is the system message, this is the user input. And based on that, this is the assistant response I'm getting. You can see we're getting a pretty detailed and a pretty crisp summary of the whole meeting. Okay, so this is the kind of output that you are able to all see. All right. Now, very interesting, the kind of prompting that we are seeing is what we often call the zero-shot prompting. That's a terminology that I wanted to use with all of you. So we have already seen 2 to 3 different types of prompts in the code now. And the kind of prompting that we have seen until now is what is called zero shot prompting. Zero shot prompting. What is a zero shot prompting? A zero shot prompting technique is a kind of prompting technique where the large language model is just responding on the basis of its pre-trained knowledge. Okay. So the large language model is just working on the basis of its pre-trained knowledge. So you take some data, you train a large language model, you train an LLM, and just on the basis of that pre-trained understanding, the LLM is working. That is what we typically refer to as zero-shot prompting. Let me give you an example to highlight this idea even further. What I mean to say, because all these language models, if you see, the GPT-4 Omni model, particularly the one that it's a very powerful model, right? It has been trained with a tremendous amount of data. So it has been trained with a lot of data. And next time you ask it some question, the GPT model will generate a response based on whatever pre-trained understanding it has. You don't need to give it some other information. It already knows. Like if I when I go and ask it, okay, what is usually the weather in Delhi? It understands it. Okay, so next time you gave it a question and you asked it, what is the sentiment of the review? It just knew it. It knew whether the sentiment is positive or negative. That is what we refer to as zero-shot prompting. So the language model is able to use its internal understanding of how things should work. That is what we generally refer to as zero-shot prompting. So let me give you another analogy. Let me give you a better analogy of what I am talking about. This is one of my favorite articles actually, which talks about zero-shot prompting in a very nice way. All of you can take a look at it. Now, if you look at this example, I have a question for all of you. Okay, the question is very simple. The question is, you have to match the following. I give you 5 symbols, and you have to tell me which of the classes does the symbol belong to. Think about it. Like, I'm sure everybody is able to answer, but think about what's going on behind the scenes. We are all human beings, right? So we can say that we are all well-trained, powerful language models, right? So each one of us in this audience, we are all like LLMs. We are all like GPT-4o. We've all been trained with 30, 35, 40, maybe in some cases 45 years worth of data. We are all well-trained models, trained on a tremendous amount of data. And we all have a very rich understanding of things. We all understand things very well. So we are all well-trained models. That's part number one. So given a generic question, we are all able to answer. Now, before you came to this class, I don't think anybody has ever seen a symbol like this. Nobody in this class came prepared that I will ask you this question, did you? I don't think anybody did, right? This was the first time in your life you're probably seeing a question exactly like this. You did not prepare for it. You did not prepare for seeing a symbol like this. But we understand that this is similar to this. Not that we studied it, but just that we have a pre-trained understanding of it. That is what zero-shot learning is all about. We are doing zero-shot learning all the time, like in these kinds of pattern matching kind of use cases. We're not prepared in advance. We are just able to use our own intelligence. We are just able to use our own generic understanding of the things around us, and we're able to answer questions, generic tasks. And language models are very good at it. Language models are very good at performing this kind of zero shot kind of thing. So much of the prompting that we saw, including the first two examples, like the summarizer we saw and the the information extraction use case that we saw is basically zero shot, because the language model inherently understands by looking at any kind of text data what is typically an age, what is typically a weight, what is typically smoking, what is typically gender, and what is typically diagnosis. The language model inherently understands that. You don't have to explicitly teach it, train it, and any of that stuff. And that's a very, very powerful attribute. Now, let me give you one more example. So zero shot learning works most of the time. It works very well. And it's a very, very good baseline that we typically use. But what are some limitations? What are some challenges? What are some limitations of zero shot learning? There must be some scenarios where we cannot use it, right? So let's talk about that. Let's talk about that. So, and you can keep going on, right? You can keep going on. Go to one more exercise. We know it, right? We know that this symbol is similar to this. We know it, right? So we know that this is similar to this. So as I told you, like before you came to the class, you didn't prepare for it, right? Now, let me give you one more use case. So the use case is, uh, let's say I'm a very well-trained model on Python. This is me, and I know Python very well. Okay, because that's the subject that we are learning and we are trying to code in Python, all that. So let's say I know Python very well. I have a very, very good understanding of Python, and I am faced with a question. The question is not this anymore. The question is like, the question that you're asking me is, add two numbers in JavaScript. Now, for those of you who don't know, JavaScript is a slightly different language. Okay, so Python is a much simpler language. JavaScript is very much like a C type of language. You have to do some other things like even declaration of variables, all that you need to do. It's pretty manual in some cases, right? Okay, there are objects and all that, so it's not exactly as easy as Python. So let's say I don't remember the JavaScript syntax that well. I know Python very well, but I do not know how to code in JavaScript. Let's say as an example. So what do I do? Will zero shot learning work now? So I'm the language model. I'm GPT-4o. You ask me a question, add two numbers in JavaScript. Can I write that program for you? Unfortunately, I can't. Okay, unfortunately, I can't. So what I need is, I just need a few examples to see. That's it. I don't have to start from scratch, spend 2 months of time, learn JavaScript, and then come back and answer the question. No. But let's just say I have enough pre-trained understanding of programming fundamentals. Let's say if I know Python very well, I already know a lot of programming concepts. Control structures, looping statements, conditional statements, operators, variables, assignments, everything I know. What is most important is the algorithm, the thought process, the thinking structure. All I need to figure out is the syntax. So the idea is, if you show me 2 or 3 examples in JavaScript, I will figure out the syntax. Okay, that's it. This is what we call few shot prompting, where you already have a very powerful language model and given a completely different task that the language model doesn't know or has never seen in the past, a slightly more specialized task. This is not a generic task like pattern matching. Pattern matching we are all able to do, right? But if it's a more specialized task, then it needs some examples to learn. And that is what we call few shot prompting. So in this case, what I will do, I will need a few examples to learn. So we will have a system message. So coming to the prompting part, we will have a system message and we will have a user assistant interaction. Few shot. This is my few shot examples. User 1, user assistant 1, user 2, assistant 2. This is my few shot examples. We will call it few shot examples. And these are the examples that the model will learn from. The system message will be add two numbers in JavaScript. User message 1 will be what? What will be the user message 1? User message 1 will be okay. Subtract two numbers. in JavaScript. And assistant one will be what? Assistant one will be the complete JavaScript code. So the idea is you're giving some examples. You're kind of teaching the LLM that if the user message was like this, subtract two numbers, the assistant response will be like this, where the complete code is I'm printing out, right? And the user message two will be something like multiply two numbers. If the user message is like this, the assistant response will be like this. And this is how I'm basically telling the large language model, which is already a very powerful pre-trained model. I'm just showing it two extra examples for it to learn better, for it to just pick up the syntax that, okay, now you just see what addition looks like, what subtraction looks like. So I give you two examples, and that entire thing is my prompt now. And I give the new user question. Remember, the new user question was what? Add two numbers. This is the new user input, right? And this entire thing is part of my prompt. I will add parameters. Remember, this is always plus parameters. We always do plus parameters. So we will do plus parameters. Parameters will be your temperature, max tokens, all those kinds of things. And this is how you make the API call. And then you get a response. And that's the idea of few-shot prompting. Few-shot prompting is a very, very powerful approach that large language models use. And it's a very, very powerful thing because even without training the model, like in this case, although I do not know JavaScript, I don't have to go back and train myself on JavaScript and come back. So even with my limited understanding of JavaScript, even with no understanding of something, just with two examples in the prompt itself, we are able to answer. And that's a very, very powerful thing, you know. So the model doesn't have to do the entire retraining. You don't have to retrain the entire language model. Retraining is a very costly process. It might take months to years of time to retrain the model with fresh data. We don't have to do that. But just by giving two to three examples in the prompt itself, you are able to kind of make the model perform very well in new tasks. And this is a very, very powerful thing called meta learning. Can you see? Model agnostic meta learning. It's called MAML. It's a particular term that we use, and it's very, very powerful. LLMs demonstrate this kind of behavior. Even without training the model specifically for certain tasks, you are able to give few examples to make the language model learn what the outcomes will be, right? To extend the conversation, and just to show you a couple of examples how it looks like, we can see these are a few examples with respect to the usage of these max tokens and all that. You can see this from the notebook. This is not very hard to do. So this is a simple example where we are trying to create a marketing uh, advertisement for the company. System messages, you're an assistant to the marketing team and help the team create an advertising content for the company. Okay. And user input is nothing but the laptop specifications. Razer Blade is a laptop. So based on the laptop specifications, your objective is to create a marketing advertisement. The only thing is that we are keeping the response limited to 200 tokens. Can you see we are saying max tokens equal to 200. So this is another one of the system parameters. Okay. So temperature we talked about. We talked about max tokens. Okay. Let's scroll down. This is temperature. You can see the temperature demo. And this is what I wanted to demonstrate. When I say temperature equal to 0.8, which is pretty high, and I also use something called n equal to 3. What is the meaning of n equal to 3? N equal to 3 means you will give three responses. Okay. For the same prompt, for the same API call, we will end up generating three responses. Three responses will come. And when I have a high temperature value, I told you already, when we have a high temperature value, remember that the variability is very high. So in three, we are getting three responses, right? And in all these three responses, we're getting three completely we're getting three completely different advertisement things. You can see the first one is different, the second one is different, and the third one is different. Okay, this is what's happening when we take a higher temperature value. On the contrary, when I take a temperature of 0, you can see we are using temperature 0, max tokens 256 because we want to use maximum 256 tokens or 256 words, and n is equal to 2. That means I want to generate two responses, and you will see that here it's exactly the same. So because the temperature is 0, you can see the responses right now that are generated is exactly the same. So response 1 and response 2 is exactly the same. It may not always be the case. Maybe there'll be some differences you will find, but here it is exactly the same, both of them. Okay, structuring prompts, few shot prompting. We already talked about it theoretically, what it is. You can see the diagram beautifully clarifies exactly what we discussed. And this is how you will structure a few shot prompt. You will give a system message, you will give some few short examples, few short guide the language model. So few short examples are what will effectively guide the language model to do the entire thing. That's what the few short examples will do. And you will give the fresh user input. And the LLM will effectively generate the outcome. So that's how the few short examples can be incorporated. Okay, just to see one example how this looks like. This is the same sentiment analysis use case we are seeing. Classify customer reviews in the input as positive or negative in the sentiment. Do not explain your answer. Your answer should only contain the label positive or negative. Let me run this. This is the system message which defines the overall behavior of your system. User input, example one. So when the review is this, the response is this. Can you see? Look at it. User input example one, the review is this. And when the review is like this, the sentiment will be like positive. You might be wondering, okay, why is it important to do it for sentiment analysis? Because sentiment analysis is such a generic use case, right? It's not necessary. The language model will inherently understand what the sentiments are. Is it positive? Is it negative? You can do it with zero shot also. But this will be typically relevant for cases where you want to fine tune the model more in line with your organization needs. Your company might have a different definition for what is positive, what is negative. Your threshold for positive or negative might be different, right? Maybe there are some companies that are more tolerant. Maybe there are certain domains where certain types of abusive words are very common. But if you go to a slightly different domain, maybe the abusive words are not very common. They are considered very bad. But if you look at some other domains, maybe certain types of words are considered very normal. So these kinds of few short prompts, these kinds of examples will help. The large language model, the LLM, is a very generic model. It has been trained on very generic data based on how things generally are. And it will do a fairly good job based on zero shot prompting. But few shot prompting is to fine tune the results more. Fine tune based on your use case, based on your organization, your domain. So you're giving it some specific examples for the LLM to learn. So you're explicitly saying that whenever the reviews look somewhat like this, the sentiment should be positive. And whenever the reviews are somewhat like this, the sentiment should be negative. And next time I have a new user review, that is your new user input. I want to generate the assistant response. And this is how you structure the complete few shot prompt. Can you see? Look at the code, all of you. Within square brackets, system, system message, user assistant, and the new user input. This is the new user input. And based on that, I will run the code. I'm taking temperature 0. And the model will generate the output response, which is sentiment positive. Straightforward. And we will see down the line how, this is a simple one with only two few shot examples, but it's not uncommon to have 10 to 100, even 100 few shot examples in a prompt. You're already starting to see how the prompt sizes can significantly increase. So the prompt is not just, okay, what is the weather today? A real world prompt can go up to several tens of thousands of tokens. And you're able to understand why. Because the prompt not just contains a user message, the prompt contains a system message, user assistant, few short examples, and it also contains the entire conversation history. So if this is part of a conversational chat, like what we were discussing a few hours back, so this entire conversation history is also part of my thread. Okay, so all the tokens are basically getting added up. Please be mindful of that. Okay, the costs are all adding up in a way. All right, all right. There's some other kinds of prompting. There's another very interesting prompting called COT prompting. And what I wanted to do at this point in time is to take you to one more very interesting link, very nice link, which talks about all these prompting techniques in a lot of detail. Let me take you to one more link here. All right, so this is the article. Actually, it's a pretty nice article. It talks about the different elements of prompting. The first part is very similar to what we talked about. And this is the part I was referring to. Zero shot, few shot, chain of thoughts, all the different types of prompting techniques are talked about here. And specifically, if you see, we have the chain of thought prompting, the few shot prompting here. And I wanted to just show this part to all of you, right? Yes, yes, I will do that. I will do that. Yes. Yeah. Yeah, I have all the links with me. I'll post it on chat in one go. Okay. So I'll post it on chat in one go. Don't worry. All right. So we have the few shot prompting. And let us see. So few shot prompting, we already saw what is the good thing about few shot prompting. We already talked about that. So the good thing is this, that you can give some more tailor-made examples. But what is the limitation of few shot prompting? What is the negative aspect of few shot prompting? The negative aspect is this. Look at the screen, all of you. Look at the left-hand side. The left-hand side demonstrates a simple few shot prompting example. And the right-hand side, to overcome the limitation, we use a different type of prompting technique called chain of thought prompting. So left-hand side, what you see is a simple example of few shot prompting. It's actually a reasoning-based question, and we are trying to solve it using a few shot prompting approach. It doesn't work. On the right-hand side, we are using something new called chain of thought prompting, where the reasoning is very clearly explained. So all of you take a look at it, give it a glance. I think everybody is able to understand generally that what's happening here is on the left-hand side, when we use few shot prompting, we are actually, especially for reasoning-based questions, you can see few shot prompting is not going to work well. Because the moment you have reasoning based questions, and if you just give input output examples, it doesn't really work. Because few shot examples is what? Few shot examples is just based on input output examples. You are trying to train the machine you're trying to train the language model based on some input output combinations, based on some input output examples. That's what few shot prompting is, right? That's the idea. The few shot prompting is just based on the input output examples. That's the whole idea of what few shot prompting is. But the problem is, when you have reasoning based questions, just having the input output examples don't help. Okay. If I say 5 plus 8 equal to 13, I cannot just say, okay, input is 5 plus 8, output is 13. Input is 7 plus 8, output is 15. But we will not learn anything from that. But what you need in these kinds of cases is you need the language model, and you need to understand, you need to explicitly understand how to go ahead and reason. So the reasoning part has to be more explicitly done. That is the whole idea. The reasoning part has to be explicitly done. And that's the whole idea of what the chain of thought prompting will do. So you can see on the right hand side, the reasoning part is more clearly explained. So the mathematics of how the solution has to be approached, the approach is more clearly explained. And which is also a big part of today. Nowadays, you see a lot of reasoning models like the DeepSeek. The DeepSeek that was released this year, early this year, it was a reasoning model, very, very powerful reasoning model. And they're all inherently based on chain of thought prompts. So the reasoning part is very clearly explained here. That's the idea. You can see the right hand side. We are not only giving the examples, but we are also giving the reasoning behind the answer. So Roger has started with 5 balls, 2 cans of 3 balls each. That means we should add. We have to explicitly tell. Don't just say answer is 11, but how did we get to the 11? That's the most important part. Okay. So this is the way chain of thought prompts actually work out. So same way we do an example here. You can see system message is given, and it's a very detailed system message. But only difference is it's a much more detailed step-by-step approach. And oftentimes at the end, we also say, explain your reasoning behind the answer. So before you present the final answer, you please tell what is the reason why you gave that answer. So that is also a very important part of the message. Okay. Another kind of prompting that is very common is a rephrase and respond kind of prompting. It's actually quite simple. All that we try to do is based on the original user input. So based on the original user input, what we do, we rephrase the original user input. That is what we refer to as rephrase and respond prompting. Because you have to understand that the users, the original users, when we talk about the users, usually the users are not the best at writing prompts, right? And we also saw that the LLMs have a lot of restrictions in terms of the number of input tokens, the total number of tokens, and all those kinds of things. So the users will also have a lot of restrictions. Users will also have a lot of restrictions in terms of like this, they will not be the best at doing things, right? That's the way to look at it. If they enter a very big input, what will happen? You will have to incur very high cost. Also, their input may not be of the best quality. So it may not be a high quality input. User prompts may not be very good quality. And if the user prompt is not of the best quality, what will happen? The accuracy of the results will be impacted. These are all real problems. These are all real problems that you have to address. And now, how do we solve it? Well, rephrase and respond. So what you can do is you can have the original prompt, whatever user is writing, take the original prompt and rephrase that prompt, maybe in 100 words. So we will use one more large language model to take the original prompt and we will rephrase the original prompt and create a new prompt. And then we will use that prompt and use it in the final LLM. This is also a very common strategy that is usually used. So oftentimes you take the original question, whatever the user input or whatever the original prompt is, you take that, you pass it through the rephrase and respond prompt, which is another language model. You can probably take an open source model for this task and you get a rephrase prompt. You take a rephrase user input. You get a rephrase prompt, which is smaller, which is shorter, which is more accurate, right? You get a rephrase prompt and now you take that prompt and then you give it to the final LLM. This is how you make the final GPT API call. You can see there are two layers we are actually using. The first layer was used to take the original user input and rephrase that into, let's say, smaller number of words. And then you use another, the final language model to go ahead and, yeah, you take the final language model to go ahead and we are effectively using it for this task. That's the way how this works out generally. And this is what we relate to as represent. Represent respond is also a very useful strategy, especially in scenarios where you have like we were discussing about this use case in the beginning, where the users will ask some question. The users will ask some question, and there are limitations in terms of the platform. There are platform limitations in terms of how big a input you can accept, because there's always a limitation and a limit in the context window, right? So you cannot have a very big context window. There are a lot of limitations that we will have in the real world. Okay, so what we need to do is we need to go and look at it. We need to go and look at it, the user limitations, and rephrase response prompting will work very, very well here. Okay, so you can have an original user input. The user input, let's say, can be 10,000 words, 20,000 words, whatever original input the user gives. And the rephrase and respond prompt will take the original user input spanning 10,000, 20,000 words, and it will rephrase that into only 100 words. And then based on those 100 words, the final thing will be taken. So that's how these kinds of things work. Because you have to understand it's always a trade-off, right? If you, let's say, imagine that you're building a customer-wise, a company-wise chatbot. Okay. If you tell that users can only enter 100 characters or 100 words, it's limiting the user's potential, right? You're actually not creating a very good experience, because users want to enter a big prompt. You don't want to limit the users. Okay, so one option is you straight away give a character limit. You say, okay, maximum you can enter 100 words. You give an input token limit. The other option is you allow the users to enter whatever they want to. Users can enter a very, very long text. They are free to enter whatever they want to. And then you can add a rephrase and respond prompting, where you can rephrase that into a slightly summarized prompt. which is more concise, more accurate, more in line with what you want to get answered. Okay, and that is what you can feed to the final language model to get your final response. So this is a very, very common strategy that is usually used. The end users will not even know that their original query is going through multiple layers, because they will just see, the input is going and they're getting a response, but they will have no idea, in terms of this working out. All right. So this is what rephrase and respond prompting is, and this pretty much wraps up this notebook. We will continue the conversation on this once again uh, in the next discussion. And there are a few other things that we will talk about, and we'll take it forward from there. The last part, I think we will just discuss is something called self-consistency. This is the last one that I will talk about, self-consistency. Very simple. And self-consistency prompting is nothing but based on a user prompt, based on a user question, we ask the LLM to generate multiple responses. Okay, so based on the user question, we ask the LLM to generate multiple responses. Let's say in this case, we ask the LLM to generate 3 to 4 to 5 unique responses. And based on that, we take the most common or the average response. So that is how this approach will work out generally. So self-consistency prompting actually works out very well, usually in cases where, so this works out very well, usually in cases, in scenarios where I would say we are dealing with very factual applications. Especially in cases where we are dealing with very factual applications, self-consistency prompting works out very well. In factual cases, factual applications where, let's say if you ask the question, what is the capital of India? Now we know the answer is supposed to be Delhi, but we know that these are also uh, word completion engines. We know these are word completion engines. So because they are word completion engines, sometimes the answer can be Delhi, sometimes the answer can be Bangalore, sometimes the answer can be something else. So there's errors. Language models are inherently, they can sometimes make mistakes. You have to keep it in mind. They can often make mistakes also, right? All these language models can sometimes make mistakes. So self-consistency prompting is a way to uh, prevent hallucinations from happening. So especially for factual applications, what you ask it a question, you give it a prompt, and based on that prompt, you generate 3 to 4 to 5 unique responses. So you ask it a question, that means you give it a prompt, you generate 5 unique responses, and based on those 5 unique responses, you choose the most common response. And that's the way how self-consistency prompting works out. So let's say even out of those 5 responses, if 4 are correct and one is not correct, let's say out of those 5 responses, 4 are correct. In 4 cases, the model says, okay, Delhi is the capital. And in one case, it says Bangalore is the capital. The most common one will be taken. So that is how, on an average, self-consistency prompting will give you the best answers, accurate answers. It is little slower because it's more compute intensive, but it will generally be more accurate because the LLM is going through multiple steps, right? So that's the idea how self-consistency prompting will work out. You can see that you ask for a set of n distinct responses, in this case, 3 distinct responses. And out of those 3 distinct responses, we can summarize the most common response. So you ask it a question, you say n equal to 5. So you ask the language model to generate 5 unique responses. And out of 5 distinct responses, you pick the most common one. You pick the response which is the most common, and this is the summarized response. So in this case, let's say if I ask the question, what is the capital of India? So even if 4 of them are correct and one of them is wrong, the more accurate one, the summarized one, the Delhi one will be taken. So even if one of case the LLM gives the wrong answer, overall, out of the 5 responses, it will give the correct answer. So that is the way how these kinds of things are used behind the scenes. So we as end users, we may not even be able to see all this, but this is what you develop in the prompt. This is all in the architecture. When developers are prompt engineers are creating the prompt, they're creating the prompt design. They are trying to create all these layers like rephrase, response, self-consistency, temperature settings, a few short examples. So we are only as end users, we are, let's say, using the ChatGPT application. We have no idea what is hidden beneath those layers. We are simply sending a user input and we are getting an assistant response, but we have no idea what are the layers that are working behind the scenes generally. Okay. All right. All right. So I think we will pause at this point in time. And what we will do is we will carry forward to the next module. So next conversation will be on, we look at some applications of how these prompt engineering techniques can be used for different tasks, particularly classification tasks, generation tasks. We will look at different tasks where these prompt engineering techniques can be used, and from there, another very important discussion area will be retrieval augmented generations, or RAGs. We'll also talk about RAGs and retrieval augmented generation, another very exciting topic area. So that's going to be the next part of our conversation.